6 divided by 2 times the quantity 1 plus 2. Type it into two different calculators or hand it to two people who both learned their order of operations cold, and it produces two different answers, both delivered with total confidence. One person says 9, another says 1. Neither one is bluffing, and neither one is wrong by the rules they were taught, and neither one is likely to back down once the other one states their case. Here is the split. One camp treats the two sitting right next to the parentheses, with no time sign between them, as glued to what follows it, a single bonded unit that has to be resolved before anything else touches it. Under that reading, 2 times the quantity 1 plus 2 becomes 6 first, and 6 divided by 6 is 1. The other camp treats that same 2, sitting right next to the parentheses, as just an ordinary multiplication, with the sign left out, no different in rank from the division sitting right before it. Under that reading, working left to right through the division and the multiplication in the order they appear gives 6 divided by 2 is 3, and 3 times 3 is 9. Both camps are following a real rule. They are just following two different real rules, and both rules show up in actual textbooks, actual journals, actual classrooms, right now, today. This isn't a trick question with one secretly correct answer hiding behind a gotcha. It is a live, ongoing, unresolved fight about how a piece of notation should be read, and math itself doesn't settle it. The stand-up comedian and mathematician Matt Parker has said basically the same thing every time this problem goes viral again, which it does every few years, on a schedule reliable enough to set a watch by. Order of operations isn't a law of the universe. It is a convention people came up with to keep expressions short and still readable, and conventions can disagree with each other. His fix is always the same one too. Write it with more brackets. Don't leave it ambiguous in the first place. It is simple advice, and it works every single time it gets followed, which is exactly why the fight only ever breaks out over expressions where somebody at some point skipped it. A close cousin of the same problem, 8 divided by 2 times the quantity 2 plus 2, makes the rounds just as regularly, splitting people the same way. One clean answer of 16 against a competing clean answer of 1, depending on the exact same juxtaposition question already covered. Neither of these viral fights would even be possible to have with the notation professional mathematics actually settled on for division, a horizontal bar with one number stacked above another. There's no left to right ambiguity hiding inside a stacked fraction, the way there is inside a line of division signs and multiplication dots, because a stacked fraction physically shows, with its own layout, exactly what's grouped with what before a single rule of precedence even needs to get invoked. The horizontal bar does double duty as its own kind of built-in parentheses, silently bundling together everything sitting above it and everything sitting below it. Structural work that a flat line of division signs and multiplication dots simply can't replicate, no matter how carefully the spacing gets arranged. The mathematics education researcher Hung-Shi Wu has pointed out that nobody in any real job doing any real calculation ever actually writes an expression shaped quite like that. He calls the whole genre of viral post a kind of gotcha parlor game built specifically to trap someone by hiding behind a pile of unreasonably tangled rules instead of testing whether they understand any real mathematics at all. That's a fair description of the internet meme. It is a considerably less fair description of the genuine, working disagreement about notation sitting underneath it. The same disagreement mathematicians, not comedians, not trick question writers, still handle differently depending on which textbook or journal they learned from. A disagreement that predates the internet, predates viral posts, predates calculators, and traces back to typographical habits that simply never got standardized across every branch of mathematics and every country at once. Professional mathematicians mostly dodge this entire argument, and they dodge it by habit rather than by rule. Past a certain level, nobody really writes a division sign or a lone multiplication dot in serious work. They stack a fraction, numerator over denominator, or they lean on parentheses until there is nothing left to argue about. The whole viral fight is really a symptom of a symbol system getting pushed past what it was built for, a shorthand invented for short expressions being forced to carry a longer one. The order of operations everyone learns as PEMDAS in the United States, parentheses, exponents, multiplication and division, addition and subtraction, or BODMAS in Britain and much of the Commonwealth, brackets, orders, division and multiplication, addition and subtraction, feels like it must be an old, settled law, handed down from Euclid or someone equally ancient. It isn't. The rule that multiplication outranks addition really did settle in early, arriving alongside modern algebraic notation back in the 1600s, since the distributive law more or less forces that ranking on its own, but the specific mnemonics, PEMDAS, BODMAS, and their cousins BIDMAS and BEDMAS were only formalized as teaching tools in the late 1800s or early 1900s. Once textbook publishers needed something standardized enough to print at scale, even the ranking between multiplication and division alone was still openly disputed among mathematicians as late as the 1920s. The historian of mathematics, Florian Caiori, pointed out that disagreement directly, noting that whether multiplication should outrank division or the two should simply be treated as equals was still unsettled among working mathematicians at the time he was writing. Those mnemonics caused their own trouble too, separate from the ambiguity already covered. Read PEMDAS too literally, and it seems to say addition always happens before subtraction, which is false. A minus B plus C has to be worked left to right, giving a different answer than doing the addition first, whenever C isn't 0. German classrooms sidestep the whole naming problem with a simpler mnemonic: dot operations before line operations, since multiplication and division are traditionally drawn as dots and multiplication signs, while addition and subtraction are drawn as flat lines, a distinction that heads off the addition before subtraction, misreading before it can even start. Education researchers have gone further and argued that leaning this hard on a mnemonic acronym at all tends to crowd out any real understanding of why the order exists, producing students. And even some student teachers who can recite the letters perfectly and still get the actual arithmetic wrong. Calculators and computers don't even agree with each other, which is its own small proof that none of this is as settled as a school worksheet makes it look. A cheap calculator without any memory for pending operations will process 6 plus 2 times 4 strictly in button press order, giving 32, while a calculator built with real operator precedence gives 14 instead, treating the multiplication as ranking higher regardless of the order it was typed in. Even the direction exponent stack gets fought over. Write 3 raised to the 2 raised to the 2 with no parentheses to settle it. And the traditional mathematical convention works from the top down, so the second exponent applies first, giving 3 raised to the fourth power. Microsoft Excel and the programming language MATLAB do the opposite, working from the bottom up, so that same expression comes out totally different in a spreadsheet than it does on paper. Excel has an entirely separate ambiguity buried in how it treats a negative sign directly in front of a number, since it ranks that unary minus as stronger than exponentiation. So the formula negative 3 squared returns positive 9 in a spreadsheet cell, while the same expression, read by the normal mathematical convention everyone was taught in school, equals negative 9, because the squaring is supposed to apply before the minus sign ever gets involved. Programming languages inherited this mess and then multiplied it. Most languages copy roughly the same precedence order mathematics uses, but not all of them, and not consistently with each other. The language APL evaluates everything strictly right to left, with no precedence levels at all, while the language Smalltalk evaluates everything strictly left to right, also with no precedence levels, meaning two entire programming languages throughout the whole idea of ranking operations and just process things in the order they're written, full stop. Dennis Ritchie, who created the C programming language, later said he regretted where he ranked the bitwise operators relative to the comparison operators, a decision that then got copied wholesale into C++, Perl, and PHP simply because those languages borrowed C's rules wholesale, regret included. Even newer languages like Python and Ruby deliberately flipped that specific ranking back the other way, undoing Ritchie's own admitted mistake decades later. There is one more wrinkle worth naming, since it shows up constantly and almost nobody notices it happening. 16 divided by 4 divided by 4. Worked strictly left to right, the way division is supposed to be handled when nothing else disambiguates it. That's 16 divided by 4 first, giving 4, and then 4 divided by 4, giving 1. Work it the other way instead. 4 divided by the quantity, 4 divided by 4, and 4 divided by 1 gives 4 right back, a completely different answer from the same three numbers and the same operation, differing only in which division gets grouped with which. Mathematicians handle this by agreeing, by convention again, not by any deeper law, that operations at the same rank get processed, strictly left to right, called being left associative, which is exactly why 16 divided by 4 is defined to mean 1 and not 4. Not every operation in every context gets grouped that way either. Programming languages that build linked lists sometimes define their list building operator to group the opposite direction, right to left, specifically because that matches how a list naturally gets built one new item at a time from the front. There is a whole notation that sidesteps every single one of these arguments at once, and professional calculators use to ship with it built in. Reverse Polish notation writes the numbers first and the operation last. So 6 divided by 2 times the quantity 1 plus 2 would get typed as 1, 2 plus 2, 6, divide times or some equivalent ordering, and every single step is completely unambiguous, since there is never a moment where two different operations are both waiting to claim the same numbers. No parentheses needed anywhere, no order of operations to memorize, no left to right versus top down argument to have. The trade-off is that almost nobody finds it intuitive to read on first exposure, which is probably the whole reason of ordinary infix notation, plus signs and times signs sitting between the numbers the normal way, worn out for everyday use, despite carrying every ambiguity already covered, built directly into it. None of this symbol set is as old as the ideas underneath it either, which is part of why the ambiguity was ever able to sneak in the first place. The equal sign first shows up in print in Robert Record's book, The Whetstone of Witte, published in 1557. The plus sign and the minus sign, along with the habit of using a plain letter to stand in for an unknown number, show up in Michael Stifel's book, Arithmetica Integra, in 1544. The very same book where Stifel called negative numbers absurd. René Descartes, in that same 1637 book that gave the quadratic formula its modern look, also popularized the convention still used today, letters near the start of the alphabet standing for known constants, letters near the end standing for unknowns, and introduced writing exponents as small raised numbers instead of spelling them out longhand. Algebra had already been doing real, correct mathematics in prose, entire equations written out in full sentences, for well over 1,000 years before any of that shorthand existed. The symbols came surprisingly late to a subject that now feels inseparable from them, and every one of the ambiguities covered in this opening stretch is really an ambiguity in that comparatively young shorthand, not in the underlying mathematics the shorthand was invented to describe. Most people meet algebra as a subject that closes doors instead of opens them, a wall of rules to be memorized and reproduced on a test. with a single correct answer waiting behind each problem, and a teacher standing by to mark anything else wrong. Negative exponents flip a fraction. A squared minus b squared factors a certain fixed way every time, no exceptions. Cross multiply to solve a proportion. None of that ever feels like it is up for debate, because none of it usually is at the level algebra gets taught in a classroom. That reputation for total, humorless settledness is exactly what makes it strange to find a live, unresolved fight sitting in the very first, simplest looking expression this whole subject can produce. Algebra gets taught like the most settled, most mechanical part of mathematics there is. Memorize the rule, apply the rule, get the answer, move on. Underneath that reputation, though, algebra is full of old fights that were never fully closed, notation that disagrees with itself, and at least one very specific proof that permanently slammed the door shut on an entire class of problems, not because nobody was smart enough to open it, but because it was rigorously shown that the door has no other side. The order of operations fight is the smallest and pettiest version of that pattern, but it isn't even close to the strangest. Negative numbers spent over 1,000 years being treated as suspicious or outright fake by mathematicians who used them anyway. Zero took centuries just to be allowed to count as a number instead of an empty space on a counting board. Those are old wounds, mostly healed by now. But there is a whole family of equations, the kind every algebra student meets by high school, where the formula that is supposed to exist for solving them has been proven, not guessed, not suspected, proven to not exist at all. And past that point, the object's algebra hands anyone working with it negative numbers, imaginary numbers, matrices. Stop behaving the way ordinary arithmetic trains a person to expect, in ways that were controversial enough to get a mathematician insulted in his own textbook. Start with the numbers themselves, since that is where the trouble starts. For more than 1,000 years, working mathematicians treated the rule that a negative number times a negative number gives a positive number as something to memorize, not something to understand. Some of them refused the whole idea of negative numbers outright. The Greek mathematician Diophantus, writing around the 3rd century, ran into an equation equivalent to 4x plus 20 equals 4. Solve it honestly, and x comes out negative. Diophantus called the equation absurd and moved on. Because of that kind of thinking, Greek geometers of the era could only solve the versions of the quadratic equation that gave positive answers. Anything with a negative solution just didn't count as a real problem to them. Other traditions were ahead of the Greeks on this by a long way. Negative numbers show up in the Chinese text called The 9 Chapters on the Mathematical Art, which, in the form that survives, dates to the Han Dynasty. Somewhere between 202 BC and 220 AD, though it may well preserve material older than that. The mathematician Liu Hoi, writing around the 3rd century, set out actual rules for adding and subtracting negative quantities. The system used two different colors of counting rods on a counting board, red rods for positive amounts and black rods for negative ones, which is the exact reverse of the modern accounting habit of writing negative numbers in red ink. Indian mathematicians were using negative numbers to represent debts by around the 7th century. Brahmagupta, writing around 630, worked out a general quadratic formula that allowed for negative numbers along the way. Islamic mathematicians picked up negative numbers from Indian sources by the 9th century, but treated them carefully at first. Al-Khwarizmi, whose book on restoring and balancing gave algebra its very name, avoided negative numbers and negative coefficients entirely. Within about 50 years, though, Abu Kamil was working out the sign rules for expanding products like the quantity A plus or minus B times the quantity C plus or minus D. And a mathematician named Al-Karaji was writing plainly that negative quantities have to be counted as legitimate terms. The mathematician Al-Samawal, writing in that same tradition in the 12th century, laid the sign rules out about as plainly as anyone before modern textbooks ever managed, stating that the product of a loss and a gain is a loss, and the product of a loss and a loss is a gain, and working out equally careful rules for what happens when a smaller debt gets subtracted from a larger one, or a debt gets subtracted from a plain gain. By the 12th century, Al-Karaji's successors had the full modern sign rules worked out and were using them to solve polynomial division problems. Meanwhile, in India, the mathematician Bhaskara II could derive negative roots of a quadratic equation just fine using the algebra of the day, and then threw them out anyway, writing that people simply do not approve of negative roots because they made no sense in whatever real-world problem the equation was describing. Europe was even slower. Fibonacci, in the year 1202, allowed negative numbers only inside financial word problems, where they could be read as debts, and later, in 1225, as losses. That is the only context where he trusted them. The 15th century French mathematician Nicolas Chuquet used negative numbers as exponents, but called them absurd numbers. Michael Stifel, writing in 1544, used the same insult, numeri absurdi, absurd numbers, for negative quantities generally. Even Girolamo Cardano, who in 1545 gave Europe its first workable treatment of negative numbers in his book Ars Magna, still would not let them into his classification of cubic equations. Instead of writing one general cubic formula the way a modern textbook would, Cardano split cubics into 13 separate cases depending on which terms landed on which side of the equal sign. Purely so, every coefficient in every case could stay positive. Even Gottfried Leibniz, generations later, still argued negative numbers were technically invalid, while using them in his own calculations anyway, because they worked. Electrical engineers today wire up a battery backward and simply call the resulting voltage negative, no philosophical crisis attached. A plain flip in the direction current wants to flow, relative to whichever direction got called positive first. Chemists track the charge on an ion, an atom that has gained or lost an electron, as a plain negative or positive number, since the electron's own charge got arbitrarily assigned a negative sign centuries after Diophantus was already calling negative solutions absurd. None of that hesitation is visible anywhere in how casually negative numbers get used today. A weather report gives the temperature as 10 below zero without a second thought. A football broadcast puts up a goal difference of -2. A golfer's scorecard reads 4 under par. A hockey player's plus minus rating goes negative on a bad night on the ice. A map's latitude reads negative south of the equator, its longitude negative west of the prime meridian. No fuss, no footnote. An elevator panel has buttons below the ground floor labeled -1 and -2. A bank statement shows an overdraft in red or wrapped in parentheses, both of which are just visual shorthand for a negative balance. None of these uses would have made obvious sense to Diophantus, who called a negative solution to an equation absurd and moved on instead of accepted, meant anything at all. It took roughly 2,000 years to get from that reaction to a species that hands a negative number to a 10-year-old checking a football score without either one of them thinking about it for even a second. Notice what actually changed across those 2,000 years and what didn't. The arithmetic itself was never the holdup. Any of these mathematicians, Diophantus included, could add and subtract perfectly well. What took 2,000 years to settle was a much softer question sitting underneath the arithmetic, whether a quantity below nothing was even a coherent thing to imagine in the first place, whether zero really was a floor or just one more marker on a line that kept going in both directions. Once that softer, more philosophical question finally got answered, the hard mechanical question, what a negative number times a negative number equals, turned out to already be sitting there, waiting, fully determined the moment the distributive law got taken seriously and applied without flinching. That pattern, a philosophical objection blocking the door for centuries while the actual arithmetic sits fully worked out and waiting on the other side of it, showed up first with negative numbers, an entire class of solutions dismissed as absurd, purely because nobody could point to 3 negative apples sitting on a table. So why does a negative times a negative actually come out positive? Most people get the rule handed to them with no reason attached, and the usual classroom shortcut that 2 negatives cancel out isn't really an explanation at all. There is a real argument underneath it, and it comes from insisting that the rules of arithmetic stay consistent with each other rather than from any deep metaphysical truth about negative quantities. Start with something everyone already accepts. A positive number times a negative number is negative. 3 debts of $2 each is a debt of $6. So 3 times -2 is -6. That much lines up with common sense. Now, bring in a rule nobody wants to give up, the distributive law, which says a number times a sum equals the sum of that number times each part. Take 2 times the quantity -3 plus 3. The part in parentheses is just 0, so the whole expression has to equal 0, since 2 times 0 is 0. Now, expand it out using the distributive law instead. 2 times negative 3 plus 2 times 3. 2 times 3 is already known to be 6, and 2 times negative 3 is already known to be negative 6. So the expression becomes negative 6 plus 6, which does equal 0. That's consistent, but it hasn't touched negative times negative yet. Try the negative version of the same trick. Take negative 2 times the quantity negative 3 plus 3. Same as before, the part in the parentheses is 0, so the whole thing has to equal 0. Expand it with the distributive law. Negative 2 times negative 3 plus negative 2 times 3. Negative 2 times 3 is already known to be negative 6, since a positive times a negative is negative. So the expression is negative 2 times negative 3 plus negative 6, and the whole thing has to equal 0. There's only one number that adds to negative 6 and lands on 0, and that number is positive 6. So negative 2 times negative 3 has to equal positive 6, not because two negatives magically cancel, but because the distributive law simply breaks, stops being reliably true. If it doesn't, there's a second, more visual way to reach the same place, and it helps to have both. Picture the number line running from negative infinity on the left to positive infinity on the right, with 0 sitting in the middle. Multiplying a number by negative 1 does one specific thing to it on that picture. Flipping it across 0 to the opposite side, 3 becomes negative 3, negative 5 becomes 5. Multiplying twice by negative 1, back to back, flips it across 0, and then flips it right back again, landing exactly where it started. Negative 1 times negative 1, worked out that way, has to equal positive 1, because two flips cancel out, just as turning around to face backward and then turning around again leaves a person facing the original direction. Negative times negative isn't a special exception bolted onto arithmetic from outside. It's what two reflections do to each other, and reflections undoing each other is about as ordinary an idea as geometry has. The sign rule for negative times negative isn't a fact about the physical world. It's the price of keeping the rest of algebra's rules from contradicting themselves. Most people are never shown that part. They are just handed the rule and told to memorize it, the same way generations of mathematicians were handed it, and for a very long time weren't shown it either. Mathematicians eventually went back and built negative numbers from the ground up out of nothing but the plain counting numbers, specifically to put that whole argument on completely solid footing rather than leaving it resting on debts and distributive laws alone. The trick is to stop thinking of a negative number as one thing and start thinking of it as a pair of ordinary counting numbers instead, a difference waiting to happen. The pair 3 and 8 read as 3 minus 8, and the pair 0 and 5 read as 0 minus 5. Both describe the exact same negative number, negative 5. So the construction lumps together every pair that describes the same difference and calls that whole bundle one integer. Addition and multiplication both get defined directly on these pairs, using only ordinary counting number arithmetic that nobody has ever doubted. And every single one of the negative number rules already covered, including the negative times negative equals positive rule, falls straight out of that definition automatically, with nothing left to simply take on faith. This same pair building technique turns out to be an entirely general recipe, not just a one-time trick for building negative numbers. And it shows up again later in this tour, doing the exact same job in a much more abstract setting. Zero has its own strange history, and it is a stranger one than negative numbers. Strange enough that a full, dedicated treatment of it belongs somewhere else entirely, well beyond what a single stop on this particular tour has room for. Briefly, here's the shape of it. Zero does two completely different jobs, and for most of history, only one of those jobs was recognized as real. As a digit, zero is a placeholder, a way of marking that a certain column in a number is empty, so that 205 doesn't get confused with 25. Babylonian mathematicians had a placeholder symbol for this by around the middle of the second millennium BC. A clay tablet dug up at the ancient city of Kish, dated to somewhere around 700 BC, shows a scribe recorded by name, Bel Ban Aplu, using three small hook marks stamped into the clay to fill exactly that placeholder role. But for a very long stretch, it was never written at the very end of a number, and it was never treated as a number capable of arithmetic on its own, only as a kind of spacer. Ancient Greek mathematics mostly rejected the whole idea outright. Greek philosophy held that there was no such thing as a void, no true nothing, and a number that meant nothing fit uneasily into that picture. The paradoxes of Zeno lean directly on how uncertain the ancient world was about what zero even meant. Greek astronomers eventually borrowed a placeholder zero anyway, purely for practical purposes, once Babylonian astronomical methods filtered into their own calculations, using the lowercase letter omicron as a stand-in for an empty degree value. The astronomer Ptolemy, writing his great astronomical work, the Almagest, around the year 150, used a small circle with a bar over it as a genuine zero symbol dozens of times over, tracking how much of the sun or the moon was covered during an eclipse, a value that legitimately needed to hit zero at the very start and the very end of the event. Even so, this was a working tool borrowed for astronomy, not a philosophical acceptance of zero as a number in its own right, and that fuller acceptance still had to wait on India. There is a real difference between a symbol that means nothing goes here and a number that behaves like every other number, sitting on the same number line, obeying the same rules of addition and multiplication, and the ancient world kept reaching for the first, without ever quite committing to the second. The idea of zero as a genuine number, something that could be added, subtracted, and reasoned about the same way 3 or 7 can be, came out of India. The mathematician Brahmagupta in the 7th century laid out actual rules for zero, including the claim that any number divided by zero produces a fraction with zero on the bottom, which isn't the modern answer, but is at least an attempt to treat zero as something computable instead of something to skip over. Later, the 12th century mathematician Bhaskara II offered a different answer, that dividing a quantity by zero produces an infinite quantity, and he described that infinite result the way he might describe an unchanging God, something that stays the same no matter how many separate worlds get created or destroyed within it. Zero's slow trip from placeholder to full number then moved through the Islamic world and into Europe by way of al-Khwarizmi, and centuries later, Fibonacci, who helped popularize the whole Hindu-Arabic number system, including zero in Europe in the year 1202. Other civilizations reached a placeholder zero on their own, entirely independent of each other, which says something about how badly positional number systems need one. Ancient Egyptian scribes used a hieroglyph read as NFR to mark days when a foodstuff received by the pharaoh's court exactly matched what got paid out, and the same symbol shows up marking the baseline in tomb and pyramid drawings, with distances measured as above or below it, a use close enough to a functional zero that at least one Egyptologist has argued it should count as one. On the other side of the world, with no possible contact between the two traditions, the Maya built a placeholder zero into the long count calendar, a positional counting system based on 20 instead of 10, and the earliest confirmed long count date using it, carved into a stone at Chiapa de Corzo in what is now Mexico, is usually dated to 36 BC. In the Andes, the Inca and earlier societies kept accounting records on knotted cords called quipu, and zero in that system wasn't a mark at all. It was an absence, a spot on the cord where a knot simply was not tied. China developed its own version through a physical counting system, small rods laid out on a counting board where an empty space between rods stood in for a missing digit, described in texts whose surviving form dates from somewhere between the 1st and 5th centuries AD. A specific round symbol for zero, looking close to a modern circle, doesn't show up in Chinese sources until the 1240s in a mathematical treatise by Qin Ju Shao, and even then, the number was still treated as marking a vacant position instead of a number in the fuller Indian sense. India moved fastest and furthest. A Jain cosmology text called the Loka Vibhaga, internally dated to the year 458, already uses a genuine decimal place value system built around zero. The mathematician Aryabhata, writing around 499, stated the core rule of positional notation directly, that each successive place is worth 10 times the place before it. A stone inscription at the Chaturbhuj temple in Gwalior, dated to 876 carries what's usually cited as the first unambiguous carved zero symbol, a small circle, and the Bakshali manuscript, an old practical arithmetic guide for merchants that uses a black dot for zero throughout, has been radiocarbon dated by the Bodleian Library to somewhere between 799 and 1102, though the different folios in the manuscript came back with wildly different ages from each other, which has kept its exact dating disputed ever since. Today, the rule is cleaner than either of those old attempts. And also, stranger, zero, is the one number where division simply refuses to work at all. Dividing by zero isn't a hard problem waiting on a clever trick. It's not defined on purpose, because letting it be defined breaks other rules, just as letting negative times negative equal negative would have broken the distributive law. Zero divided by zero is even worse. It doesn't even get called undefined so much as indeterminate, meaning the answer depends on exactly which direction zero got approached from, and calculus students spend real class time on exactly that problem, approaching the same troublesome ratio from different directions and watching it settle on different answers, depending purely on the path taken toward it. An uncomfortable idea the first time it gets seen, that a single expression can behave like several different numbers, depending on how it gets approached, instead of settling on one fixed value, the way every other number always has. Physics treats zero unevenly too, depending on what's being measured. Absolute zero really is a hard floor, the coldest a physical system can possibly get. Nothing colder exists to reach for. A thermometer reading negative temperatures relative to that absolute floor is really doing the exact same conceptual work the number line does relative to the ordinary zero already covered earlier in this stretch, marking a direction and a distance from a fixed reference point instead of describing some kind of true absence. A temperature of zero on the Celsius scale, by contrast, is a completely arbitrary marker, just the freezing point of water at sea level, with plenty of colder temperatures sitting comfortably below it. Sound measured in decibels sets its own zero point arbitrarily too, pegged to the quietest sound an average human ear can detect, not to an absence of sound waves at all. Three different zeros. One, an absolute physical floor. Two, just convenient markers a person picked. That mix, one genuine hard limit, sitting right alongside two totally arbitrary labels, all written with the exact same symbol, is a big part of why zero confuses people well into adulthood in ways 2 and 7 never do. And it shows up in ordinary calendars too, one of the quieter, more persistent sources of confusion the number causes. There is no year zero in the calendar. Most of the world uses day to day. The year before, year 1 AD, is simply called 1 BC, with nothing numbered zero sitting in between them, which routinely trips up anniversary calculations and centenary celebrations alike, since the jump from 1 BC straight to 1 AD is a jump of exactly 1 year, not two, no matter how tempting the arithmetic looks at first glance. Nobody wonders whether the number 7 means something different in a temperature reading than it does in a bank balance. 0 gets asked to be an absolute floor in one context and a purely relative bookmark in another, without ever announcing the switch. And the symbol never changes to warn a person which job it's doing this time. Even biologists have gotten interested in 0 for its own sake, well outside mathematics entirely, a strange kind of company for a placeholder mark on a Babylonian scribe's clay tablet to eventually keep. Certain animals have been shown in careful experiments to display something recognizable as an awareness of 0 as a quantity, treating an empty set as meaningfully different from a small non-zero one instead of simply ignoring it, which some researchers in comparative zoology and cognitive science take as evidence that the capacity for this particular kind of numerical abstraction reaches back much further into evolutionary history than anyone might have guessed. From watching only humans struggle with the idea for millennia. If some corner of the animal kingdom already grasped the concept intuitively, the puzzle stops being why 0 is hard and starts being why it took human civilization so long, spread across so many independent attempts to catch up to what may have been sitting in front of it the entire time. At the same time, 0 runs the entire rest of arithmetic from behind the scenes. Add 0 to anything, and nothing changes. That property has a name, the additive identity, and it shows up in a couple of places that trip people up on first exposure. Add together a whole list of numbers with nothing on the list at all, and the total, by convention, is 0, the empty sum. It's the only answer that keeps every other rule of addition from breaking. The same kind of forced consistency that settled negative times negative earlier in this tour. 0 turns out to be one of the load-bearing pieces underneath algebra's later, much more abstract structures, the kind that show up only once the question shifts from what numbers are to what rules. A whole system of numbers has to obey. 0 still causes fights in unexpected places even now. Every piece of software running on a phone or a computer has to pick whether the first item in a list gets labeled item number 1 or item number 0, and different programming languages picked differently, with real consequences for anyone switching between them. The language, Fortran, one of the oldest still in use, starts counting at 1, the way most people count things by hand. The language C, and most of what descended from it, starts counting at 0 instead, a choice that traces back to how C actually stores a list in memory as a starting address plus an offset, and the very first item naturally sits at an offset of 0 from itself. That mismatch has caused real working bugs for as long as programmers have had to move code between languages that disagree about it. Computers also mark time from an arbitrarily chosen 0 point, an epoch, and the most common one used by practically every phone and server on Earth, sets the 0 point at midnight on the 1st of January, 1970. None of that the order of operations fight, the centuries of side-eyeing negative numbers, zero's long climb to being a real number is really about numbers themselves. It's about notation, about how humans choose to write things down and what counts as an acceptable move once they have the stranger. Part of algebra isn't about how an expression gets written. It's about what can be solved at all. And it turns out some things provably can't be, not because nobody has found the trick yet, but because the trick has been formally and permanently proven not to exist. The quadratic equation is the first place most students meet that idea, an equation with an x squared in it, written in the general form ax squared plus bx plus c equals 0, where a, b, and c stand for whatever numbers happen to be in front of each term, and a is never allowed to be 0, or the x squared disappears and the whole thing stops being a quadratic at all. Every algebra class eventually hands over the formula for solving it. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Plenty of people memorize that string of symbols for a test and never once ask where it came from, which is a shame because where it comes from turns out to matter for everything that follows. The method behind it is called completing the square, and it is ancient. Babylonian clay tablets already contain problems that reduce to solving quadratics. The Egyptian Berlin papyrus, which dates from somewhere in the Middle Kingdom, contains a solved two-term quadratic. Euclid solved quadratics geometrically with actual diagrams of squares and rectangles in the second book of his Elements, sometime around 300 BC. The Chinese nine chapters has quadratic rules from around 200 BC as well. Diophantus, a few centuries later, solved quadratics in something closer to modern algebraic style, but his method only ever produced one root, even in cases where the equation had two positive solutions available. Brahmagupta, in India around 628, gave a general method for finding one root, written out entirely in prose instead of symbols, the way math was written at the time. An 8th or 9th century Indian mathematician named Sridhara worked out a version of the method that avoided fractions almost entirely by multiplying through by 4 times a instead of dividing by a. And that specific trick is still sometimes called Sridhara's method today. And in parts of India, the whole quadratic formula still carries his name, called Sridharacharya's formula, the same way it gets called Bhaskara's formula in parts of Brazil after the later Indian mathematician Bhaskara II. One formula wearing 3 completely different names depending purely on which country happened to be teaching it. Al-Khwarizmi in the 9th century solved quadratics algebraically as well. The version of the formula that handles every possible case in one sweep, positive coefficients, negative coefficients, all of it in one unified formula, was first put together by Simon Stevin in 1594. Descartes, in his book La Géométrie, published in 1637, wrote out special cases of the formula in something close to the notation still used today. The actual derivation is short enough to walk through cleanly. Start with a x squared plus bx plus c equals 0. Divide everything by a, so the x squared term has no coefficient in front of it anymore. Move the plain number term to the other side of the equation. What's left on the left side looks almost like a perfect square already. X squared plus some multiple of x. And there is a specific number that can be added to both sides to finish turning it into an actual perfect square, a squared binomial. Add that number in, and the left side becomes a single squared quantity, x plus something, all squared. Take the square root of both sides, remembering that a square root has two possible signs, and then isolate x. What falls out the other end is exactly the quadratic formula. Every step in that derivation is just algebra. Anyone who has finished a first year of the subject can follow. Nothing about it is a trick. It works every single time for every quadratic equation that exists, no exceptions, and mathematicians have known it works since before Europe had modern algebraic notation to even write it down cleanly. The quantity under the square root b squared minus 4 ac has its own name, the discriminant, and it signals what kind of answer is coming before the calculation is even finished. If it comes out positive, the equation has two separate real number solutions. Run one plain, friendly example through the whole machine to see it land. Take x squared minus 5x plus 6 equals 0. Here, a is 1, b is negative 5, and c is 6. The discriminant b squared minus 4ac works out to 25 minus 24, which is 1, a clean positive number. So two separate real solutions are guaranteed before any further arithmetic even happens. Plug everything into the formula and x equals 5 plus or minus the square root of 1 all over 2, which simplifies down to 5 plus 1 over 2, or 5 minus 1 over 2, giving exactly 2 and exactly 3. Check it directly against the original equation, and it holds up instantly. 2 times 3 is 6, and 2 plus 3 is 5, matching the coefficients sitting right there in the original equation. Since a quadratic with roots 2 and 3 always factors as the quantity x minus 2 times the quantity x minus 3, which multiplies back out to x squared minus 5x plus 6, the exact equation this whole example started from. If it lands exactly on 0, there is one repeated solution. And if the discriminant is negative, meaning it's asking for the square root of a negative number, something that doesn't exist among the real numbers at all, the equation still has two solutions. They just aren't real numbers anymore. Hold that particular wrinkle in mind. It comes back later, and it comes back in a much bigger way than a footnote. There is a second way to derive the exact same formula, one that looks completely different on the surface and turns out to matter far more than the completing the square method does later on. Instead of manipulating the equation itself, focus entirely on the two roots. Call them alpha and beta, and build two specific combinations out of them, their sum and their difference. The sum, alpha plus beta, stays exactly the same no matter which root gets called alpha and which gets called beta, so it can always be written cleanly in terms of the equation's plain coefficients, with no square roots needed at all. The difference, alpha minus beta, flips its sign the instant the two labels get swapped, so it can't be written that cleanly, but its square can, since squaring erases the sign flip, and that square does reduce down to the familiar discriminant. Recover the individual roots by adding and subtracting those two building blocks back together, half the sum plus or minus half the difference, and the quadratic formula falls straight out the other end. Those two building blocks have a name, Lagrange resolvents, after Joseph Louis Lagrange, and the same basic trick, watching which combinations of the roots stay fixed when the roots get shuffled around, and which combinations flip, extends to cubic equations and to quartic equations, each time producing a smaller equation that can be solved first and then used to unlock the original one. Push that same idea 1 degree further to a quintic, and the resolving equation it produces has degree 24, which doesn't make the problem easier, it makes it worse. And that breakdown is an early hint of exactly why a general fifth degree formula turns out to be a fundamentally different kind of problem, not just a harder version of the same one. It took until 1594 for one single version of the formula to cover positive and negative coefficients together, which is a strange amount of time given how early the underlying method, completing the square, had already been worked out across so many separate civilizations. What actually slowed things down for so long was not the mathematics itself, but the discomfort with negative numbers already covered earlier in this tour, since a formula meant to cover every possible sign combination could not be fully unified until negative coefficients were trusted enough to sit inside it without the mathematician needing to split the problem into separate cases first. There is also a real practical wrinkle hiding inside a formula that looks perfectly exact on paper. The quadratic formula is exactly correct only when using the idealized infinite precision arithmetic of pure mathematics. Hand it to a real calculator or a real computer, working with a fixed number of digits, and it can return a badly wrong answer, even though every single step looked correct. Take the equation x squared minus 1634x plus 2 equals 0 and run it through a calculator carrying 10 digits of precision. One of the two roots comes back essentially perfect. The other one comes back with only about 4 correct digits, a real measurable loss of accuracy, even though the calculator did nothing wrong by its own internal rules and followed the formula exactly as printed in any textbook. In a setting where that missing precision actually matters, engineering calculations feeding into a physical structure or a financial model tracking real money, 4 correct digits instead of 10 isn't a rounding curiosity. It is the kind of silent error that can compound across thousands of repeated calculations before anyone notices the answer has drifted. The problem is that the formula asks for negative b minus the square root of the discriminant. And when b is close in size to that square root, subtracting two nearly equal numbers wipes out most of the meaningful digits in the result, a phenomenon numerical analysts call catastrophic cancellation. There is a fix, a lesser known second version of the formula, sometimes nicknamed Citardok, which is quadratic spelled backward, that puts the square root in the denominator instead of the numerator, and swapping to that version for whichever root would otherwise trigger the cancellation restores the missing precision completely. Two formulas, both mathematically exact, both proven correct centuries ago, and only one of them safe to trust on any given route once real finite precision arithmetic gets involved. There is also a quick, cheap sanity check built directly into the formula's own structure, useful anywhere A and B and C stand for actual physical quantities instead of plain numbers, feet, seconds, dollars, whatever the problem happens to be measuring. Since ax squared and bx get added together inside the original equation, they have to be measuring the exact same kind of thing, which forces x itself and the ratio of b to a to share matching units. That same logic pins down what c has to be measuring to, purely from the structure of the equation, before a single number gets plugged in. A physicist or engineer who sets up a quadratic equation and finds the units refusing to match up that way has almost certainly made a setup mistake somewhere upstream. And the formula catches it before a single root ever gets calculated. There is also a cubic formula for equations with an x cubed in them, and it was worked out during the 1500s by an overlapping cast of Italian mathematicians, Scipione del Ferro first, though he never published, then Niccolo Fontana Tartaglia independently a bit later, who shared his method with Cardano under a promise of secrecy that Cardano eventually broke once he learned Del Ferro had beaten Tartaglia to it. Cardano published the whole thing in his 1545 book Ars Magna, and his student Lodovico Ferrari worked out the quartic formula for equations with an x to the fourth power, which got published in the same book. So, by the middle of the 1500s, mathematicians had complete general formulas for degree 1, degree 2, degree 3, and degree 4 equations. Each formula was uglier and more complicated than the last, involving nested roots inside roots. But each one existed, and each one worked on every equation of that degree, no exceptions, the same way the quadratic formula does. The obvious next move was to keep going. Find the formula for degree 5 equations, the quintics. Every earlier jump from degree 1 to 2, 2 to 3, 3 to 4 had come with real difficulty attached, but had still eventually given way. There was no obvious reason sitting in plain sight to expect degree 5 to behave any differently, and plenty of serious mathematicians spent real portions of their working lives convinced the formula was still out there, just one clever substitution away. Mathematicians spent roughly 250 years on exactly that problem, and they got nowhere, which starts to look less like bad luck the longer that stretch of failure goes on. Carl Friedrich Gauss appears to have been the first person to suspect why, and he suspected it early in 1798, years before he would publish almost anything. In a private section of his book Disquisitiones Arithmeticae, which itself was not published until 1801, Gauss wrote that he had little doubt the problem of solving the general equation algebraically was not simply defying every method modern analysis could throw at it, but was instead proposing something flatly impossible. That is a strange thing for a mathematician to write down in 1798. Most working mathematicians assume an unsolved problem is just waiting for someone clever enough. Gauss was apparently already suspecting the opposite, that no one would ever solve it because there was nothing there to solve. He never published anything more on the topic himself. The first real attempt at an actual proof came from Paolo Ruffini in 1799. Ruffini's key insight, and it was an important one, was to stop looking at individual numbers involved in solving the equation and start looking at permutation groups, the different ways the roots of the equation could be shuffled around while still preserving every true mathematical relationship between them. He sent his proof out to several leading mathematicians, hoping for it to be acknowledged. Lagrange never replied at all. Augustin Louis Cauchy wrote back that he believed the memoir conclusively proved the algebraic unsolvability of general equations above the fourth degree, praise from a serious mathematician. But most others were not convinced, and it turned out they were right not to be, because Ruffini's proof had a real gap in it, one that was not fully identified until much later. He had assumed that any radical expression showing up in a hypothetical solution would have to be built entirely out of the roots of the equation itself, using only the four basic operations, which sounds reasonable but isn't actually guaranteed. And there are concrete cubic equations where it demonstrably fails to hold. Niels Henrik Abel himself later wrote that Ruffini's memoir was so complicated it was very hard to judge whether the argument was even valid, and that he was not personally satisfied it was. Abel closed the gap in 1824 in a proof he compressed down to just 6 pages, printed at his own expense, because he did not have money to spare and wanted to save on paper. A longer, more fully worked out version followed 2 years later. What Abel actually proved is that there is no general formula built from addition, subtraction, multiplication, division, and roots of any order that solves every degree 5 equation, the way the quadratic formula solves every degree 2 equation, not a formula nobody has found yet, a formula that has been shown by rigorous proof to not exist, just as it has been shown that there is no largest prime number, a fact Euclid nailed down more than 2,000 years before Abel was even born, using nothing more than a short, clean argument by contradiction. Both proofs share the exact same flavor. Neither one works by exhausting every possible case and watching each one fail. Both work by assuming the impossible thing is possible after all, and then following that assumption logically until it collapses in on itself. This doesn't mean every single quintic equation is hopeless. Some specific quintics absolutely can be solved with radicals. The equation x to the fifth minus 1 equals 0 being 1. Easy example, since its solutions are related to the fifth roots of unity, and those have known formulas. What Abel proved is that no single formula exists that handles every quintic equation in one shot, purely from its coefficients, the way the quadratic formula handles literally every quadratic that could ever be written down. There's a genuine practical relief buried inside a result that sounds purely negative on its face. Modern computer algebra systems, the software mathematicians and engineers actually run today to solve equations, never waste a single cycle hunting for a general radical formula for a degree 5 or higher polynomial, because Abel already closed that door permanently nearly 2 centuries ago. Instead, those systems reach straight for numerical approximation methods, techniques that home in on a root by successive, repeated estimation, starting from a rough guess and refining it step by step until the error shrinks below whatever tolerance the situation demands, rather than by writing down an exact closed formula. And they do that with total confidence, not because an exact formula happens to be hard to find that particular week, but because a proof, sitting in the background the whole time, already guarantees no amount of additional searching by anyone using any amount of cleverness or computing power would ever turn one up. A proof of impossibility, it turns out, can save more collective effort than almost any proof of possibility ever could, since it permanently tells an entire field exactly where to stop looking. The theorem stayed under the name Abel-Ruffini, not Abel alone. Even after all of this, Ruffini's flawed attempt came first in 1799, and the standard modern name keeps his effort attached to the result, even though the actual, complete, gap-free proof belongs to Abel. Mathematics does that occasionally, keeping an earlier, incomplete name pinned onto a later, finished proof, as a kind of historical marker of who got there first, even without quite making it all the way. The proof itself got revisited more than once after Abel. Pierre Wansel, the same mathematician who would go on to settle the ancient geometry problems covered next, published a simplified version of Abel's argument in 1845, already working with a clearer sense of how Galois's newer methods connected to it. And more than a century after that, in 1963, the mathematician Vladimir Arnold found an entirely different proof, built from topology instead of algebra, tracing how the roots of a quintic equation braid around each other as its coefficients get varied continuously, a proof that opened up an entire new field afterward, called topological Galois theory. that still left an obvious loose end. Given one specific quintic equation sitting on the table, how would anyone actually tell whether that particular equation happens to be one of the solvable ones or one of the ones with no radical solution at all? Abel was reportedly working toward a full answer to that exact question when he died in 1829 at 26 years old. The complete answer came from someone else, someone even younger. His name was Évariste Galois, and in 1830, at 18 years old, he submitted a memoir to the French Academy of Sciences laying out his theory of when equations could and could not be solved by radicals. The Academy rejected it in 1831 on the grounds that it was too sketchy and gave its condition in terms of the roots of the equation rather than its coefficients, which was, in a sense, missing the point of what made the work new. Galois died the following year in a duel at 20 years old. His memoir, titled Memoir on the Conditions for Solvability of Equations by Radicals, sat unpublished for 14 years after his death, until Joseph Louville finally published it in 1846, adding his own explanatory notes to help other mathematicians follow it. Louville had actually announced the result to the Academy in a speech 3 years before that, in 1843, ahead of the full publication. Even then, the ideas took a long time to sink in. Louville's own published commentary from 1846 completely missed the group theoretic core of what Galois had actually done. Arthur Cayley in Britain failed to grasp the depth of it for years, and the standard British algebra textbooks of the era did not even mention Galois' theory until well after the turn of the 20th century. What Galois actually saw, that Abel and Ruffini had not, was a way to look past the specific numbers involved in solving an equation and study the shape of the relationships between the roots instead. Here is the idea in its simplest form. Take a quadratic equation, x squared minus 4x plus 1 equals 0. Run it through the quadratic formula, and the two roots come out to 2 plus the square root of 3 and 2 minus the square root of 3. Call those two roots a and b. Now notice something. A plus b equals 4, a clean whole number, no square roots left in it at all, and a times b equals 1, another clean whole number. Both of those combined expressions, the sum and the product, are what mathematicians call symmetric, meaning swapping a and b, trading the plus square root of 3 root for the minus square root of 3 root, and vice versa, leaves both expressions exactly the same as before. A plus b is still 4, no matter which label goes to which root, and a times b is still 1 either way. But looking instead at the expression a minus b, swapping the labels flips its sign. Since 2 plus root 3 minus 2 minus root 3 is a different number than 2 minus root 3 minus 2 plus root 3. That one isn't symmetric, and there's a reason it isn't. It involves the square root of 3 by itself, a coefficient that isn't a whole number, not a rational number. And mathematicians only allow themselves to swap roots freely when the resulting expression still stays built entirely out of rational coefficients. The set of every way the roots of an equation are allowed to be shuffled around while still preserving every one of those true rational relationships between them is called the equation's Galois group. For that particular quadratic, the Galois group has exactly two members. Leave the roots alone or swap them. That's it. For a quartic equation, Galois worked through, as an example, x to the fourth minus 10x squared plus 1. The four roots involve both the square root of 2 and the square root of 3 combined in different sign patterns. And the Galois group this time has four members, corresponding to flipping the sign on the square root of 2, flipping the sign on the square root of 3, flipping both together, or flipping neither. That four-member group has a specific structure, one that mathematicians call the Klein-4 group, and it turns out that specific structure is exactly why the quartic formula exists at all. Walk through that quartic example a little more slowly, because the pattern is worth actually seeing instead of just being told about. The four roots are the square root of 2 plus the square root of 3, the square root of 2 minus the square root of 3, the negative of the square root of 2 plus the square root of 3, and the negative of both added together. The equation itself, x to the fourth minus 10x squared plus 1, comes from an unusual, almost sideways version of completing the square, treating the whole expression as a squared quantity, minus 8x squared, which factors into two quadratic pieces once the square root of 2 gets allowed into the coefficients, and running the ordinary quadratic formula on each of those two pieces separately is what finally produces all four roots. Every one of those four roots is built from exactly the same two ingredients, the square root of 2 and the square root of 3, combined with one of four possible sign patterns, plus, 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 minus, minus, plus, minus, minus, swapping which root gets which label while keeping every true rational relationship between them intact, turns out to correspond exactly to flipping one or both of those two signs, and nothing else is allowed, since any swap that tried to do something stranger would break some rational relationship the roots are required to keep satisfying. Four sign patterns, four allowed swaps, a Galois group with exactly four members in it, and that group happens to be built the same way as flipping a light switch and flipping a second independent light switch. Each flip undoing itself, both flips commuting freely with each other. That specific four-member structure, called the Klein-4 group, is about as gentle and unbreakable as a group can be. And gentle, breakable groups are exactly what a radical formula needs to exist. Galois himself described all of this in terms of swapping roots around, which is how his original memoir was written. But modern mathematicians usually tell the same story in a slightly different, more general language, the language of field extensions already touched on briefly with straight edge and compass work. In that retelling, the Galois group isn't a set of swaps at all formally. It's the set of every way of relabeling the bigger field built by tossing all of a polynomial's roots into the rational numbers, while leaving the plain rational numbers themselves completely untouched. That reframing does the same job as the swapping description, but it comes with a powerful bonus attached: a clean, exact, two-way matching between every smaller field sitting inside that bigger one and every subgroup sitting inside the Galois group, so that questions about towers of number systems and questions about the internal structure of a single finite group turn out to be, quite literally, the same question asked in two different vocabularies. That matching has its own name, the fundamental theorem of Galois theory, distinct from the fundamental theorem of algebra covered earlier, and it's the single piece of machinery that turns Galois' whole approach from a clever trick about one type of equation into a general tool mathematicians still reach for constantly. In settings that have nothing to do with quintics at all, number fields built by adjoining roots of polynomials to the rational numbers, the way this whole tour has been doing since the compass and straight edge stretch, are the actual objects. Modern algebraic number theory studies most closely, and the ring of algebraic integers living inside a given number field. The same kind of object Hilbert was thinking about when he coined the word ring in the first place is exactly the setting where questions about prime factorization stop being as clean as they are among the plain integers. Not every field extension earns the right to be called a Galois extension either, and the two extra conditions it has to pass are worth naming, since they're really just careful ways of ruling out cheating. An extension counts as normal if, whenever it contains even one root of some polynomial, it's forced to contain every single one of that polynomial's other roots too. No picking and choosing only the convenient ones. It counts as separable if no polynomial involved ever has a repeated root hiding inside it, no two roots secretly collapsing into the exact same value and shrinking the group of available swaps. An extension satisfying both conditions at once, normal and separable together, is a Galois extension, and it's precisely the setting where that whole elegant correspondence between subfields and subgroups is guaranteed to hold up cleanly. Push far enough past ordinary numbers, and this same field extension machinery keeps working in settings that don't look numerical at all. Take every function that behaves well almost everywhere on some smooth, curved surface, a Riemann surface, tolerating a small number of well-behaved blow-ups called poles, and that whole collection of functions itself forms a field, one that sits as an extension over the plain complex numbers. Exactly the same relationship already covered between the rational numbers and the square root of 2. Field extensions were never really about numbers specifically. They were always about one system sitting cleanly on top of a smaller one, and numbers just happened to be the first place mathematicians noticed the pattern. Here is the payoff, the part that actually answers Abel's leftover question. Galois showed that an equation is solvable using radicals exactly when its Galois group has a particular property called being solvable, which is a technical way of saying the group can be broken down step by step into a chain of smaller pieces, where each step in the chain is, in a specific formal sense, as simple as possible, cyclic, for every equation of degree 4 or lower. No matter how complicated the coefficients get, the Galois group always turns out to have that solvable property. That is the real underlying reason the quadratic, cubic, and quartic formulas exist. Not because mathematicians got lucky finding them, but because the group of symmetries hiding underneath those equations happens to be simple enough every single time to be untangled by radicals. For degree 5 and higher, that guarantee breaks. The full symmetric group on 5 things, meaning every possible way of shuffling 5 objects around, contains a piece inside it called the alternating group. And starting at degree 5, that alternating group stops having the nice breakable structure that lower degree symmetric groups have. It becomes what is called simple in the technical sense, meaning it can't be broken down any further at all, and it isn't built out of cyclic pieces the way a solvable group needs to be. Once that piece shows up inside the Galois group of an equation, there is no chain of radicals that can possibly unwind it. It helps to slow down and actually feel why 5 is the specific number where the wheels come off instead of 4 or 6 or any other number nearby. With 2 roots, there is exactly one non-trivial way to shuffle them, swap the pair, and that lone swap is automatically its own undo, harmless, small, easily absorbed into a solvable chain. With 3 roots, 4 roots, the shuffles multiply, but they still all manage to organize themselves into a tidy, nested sequence of smaller and smaller pieces, each layer breakable into the layer below it, all the way down to nothing. Once 5 roots are on the table, the sheer number of ways to shuffle them, 120 in total, finally gets large enough and tangled enough to contain an unbreakable knot inside it, a piece that can't be split any further and refuses to be built purely out of the simple, cyclical steps a solvable chain needs. 4 objects apparently don't leave enough room for that knot to form. 5 is exactly the threshold where there's finally enough space for one to tie itself. That is the actual mechanism underneath Abel's proof, made completely explicit. The reason no formula exists for the general quintic is that starting at degree 5, an unbreakable knot shows up in the symmetry structure of the roots, one that simply isn't there for lower degrees, and radicals are provably the wrong tool for untying that particular kind of knot. Better still, Galois' method doesn't just explain why the general formula fails. It gives an actual test that can be run on one specific quintic equation to find out whether that one equation happens to be solvable or not, the exact question Abel died still chasing. The mathematician Arthur Cayley later worked out a shortcut for this test called Cayley's resolvent, a degree 6 polynomial built directly out of the coefficients of the quintic in question. Plug the numbers in, and if the resulting degree 6 polynomial happens to have a rational root, the original quintic is solvable by radicals. If it doesn't, it isn't. One specific example makes this concrete. The equation x to the fifth minus x minus 1 equals 0 looks almost embarrassingly simple, and it has no rational roots itself. And its Galois group turns out to be the full, unbreakable, symmetric group on 5 things. It is, in fact, about the simplest possible example of a quintic that provably can't be solved by any radical expression whatsoever, no matter how many nested roots get stacked up. There is a clever shortcut for confirming that particular claim, one that never has to touch a single actual root of the equation. Reduce that same equation, x to the fifth minus x minus 1, so that every coefficient gets replaced by its remainder modulo 2, back to the same clock arithmetic already sitting patiently a few minutes ahead in this tour, and the reduced equation happens to break apart into 2 smaller pieces, one of degree 2 and one of degree 3. That factoring pattern means the Galois group has to contain some element built out of a 2-step cycle glued to a 3-step cycle, and squaring that particular element isolates a plain 2-step swap, a transposition, on its own. Reduce the same original equation modulo 3 instead, and this time it refuses to factor at all. It stays whole, which means the Galois group also has to contain some element that cycles all 5 roots at once, a 5-step cycle. A transposition and a 5-step cycle together are enough by themselves to generate every single one of the 120 possible ways of shuffling 5 objects, the full symmetric group with nothing left over, and a 120 element group that large and that unbroken is exactly the kind of group Galois' theory rules out from ever being solvable, since a 5-step cycle and a plane swap together generate far too much internal structure for the group to ever break apart into the tidy cyclic chain a radical formula would need. None of that argument needed to know what the actual roots of the equation looked like. It only needed to know how the equation behaved on 2 small, finite clocks. Modern computers can now run this kind of test on much higher degree equations, checking solvability for polynomials of degree over 100. But even for the plain degree 5 case, when a quintic does turn out to be solvable, the actual radical expression for its roots is so enormous, so many layers of nested roots deep, that it has no real practical use, even once it's finally in hand. Galois-handed mathematics, a permanent yes or no answer to a 250-year-old open question, using a piece of machinery, the idea of a group that he had to invent from scratch to even ask the question properly. There's a question sitting on the other side of Galois' whole idea that mathematicians still have not fully closed out, almost 2 centuries later. Given some particular group, can a mathematician always go find an equation whose Galois group turns out to be exactly that one? For plenty of groups, the answer is a clean yes. And it has been known to be a clean yes across the board for one broad category, every solvable group since the 20th century mathematician Igor Shafarevich proved it. But the fully general version of the question, whether literally every finite group whatsoever shows up as somebody's Galois group over the rational numbers, is still open, an open problem sitting directly on top of the same idea Galois invented before he turned 21. Mathematicians have gone as far as constructing a specific equation whose Galois group is the monster group, one of the largest and strangest of the finite simple groups. A group with roughly 8 times 10 to the 53 elements in it, larger than the number of atoms making up the earth, a number so far past ordinary intuition that comparing it to atoms is really just a way of admitting no everyday comparison actually helps. Representation theory, a branch of group theory concerned with letting an abstract group act directly on a vector space, ties the two structures covered so far in this stretch of the tour together explicitly, translating an abstract group's own internal rules into ordinary matrix multiplication so that abstract questions about a group can be answered with concrete, computable arithmetic instead. Group theory even predicts things about ordinary physical materials that would be hard to guess any other way. When a material shifts from one crystal structure to another, say cooling through what's called its Curie temperature and flipping from a symmetric, non-polarized state into a lopsided, electrically polarized one, group theory can predict which physical properties are forced to change at that exact moment and which ones are protected purely from tracking how the symmetry group of the crystal structure shrinks as the material passes through the transition. The same basic logic, tracking a symmetry that breaks, connects all the way up to elementary particle physics, where this same kind of spontaneous symmetry breaking is tied directly to the appearance of a specific class of particles called Goldstone bosons, particles predicted in principle purely from tracking which symmetries survive a transition and which ones get lost along the way. Galois's memoir asked mathematicians to check something specific about the group of symmetries hiding in an equation's roots, whether that group could be broken apart into a particular kind of chain, instead of asking them to check anything about the coefficients sitting plainly in front of them, which is exactly the kind of request that gets a paper rejected by referees looking for something more familiar. He was 20 years old when he died, and it took the mathematical world the better part of the following half-century to fully understand what he had actually handed them. Joseph Alfred Serre finally worked Galois theory into a mainstream French algebra textbook in 1866, 3.5 decades after the duel. Serret's own student, Camille Jordan understood the material well enough by 1870 to write an entire treatise built directly around it. Richard Dedekind was already lecturing on Galois theory at Göttingen by 1858, showing a real working grasp of it well ahead of most of his contemporaries. And Heinrich Martin Weber's Algebra textbook, published in 1895, is generally credited with the version of the theory that finally made it accessible to a wide audience of students instead of just a handful of specialists. From one rejected memoir by an 18-year-old to a standard part of the undergraduate curriculum took the better part of a full century. The same shape of impossibility, provable rather than merely undiscovered, shows up again in a completely different corner of mathematics, one that on the surface looks like it has nothing to do with equations at all. Geometry done with nothing but an unmarked straight edge and a compass. The ancient Greeks worked out an enormous amount using just those two tools. They could bisect any angle. They could construct a square with exactly twice the area of another square. They could build regular polygons with 3, 4, or 5 sides and double the number of sides of any polygon they already had. But there were a small handful of problems they could never crack, no matter how many centuries they threw at them. Trisecting an arbitrary angle, cutting it into 3 exactly equal pieces, using only the straight edge and compass. Doubling the volume of a cube, meaning building a new cube with exactly twice the volume of a given one, using only those same 2 tools. And squaring the circle, constructing a square with exactly the same area as a given circle. It was never for lack of trying. Either Hippocrates and Menaechmus both worked out ways to double a cube's volume by intersecting curves called hyperbolas and parabolas, real, valid solutions, just built from tools that reach further than a bare straight edge and compass are allowed to reach. Hippias, in the 5th century BC, invented an entirely new curve called a quadratrix, specifically to trisect an angle and to square a circle. And it worked for the same reason. Extra tools beyond the 2 allowed ones. Nicomedes, a couple of centuries later, used a curve called a conchoid to trisect an angle as well. Every one of these mathematicians solved the actual problem. None of them solved it within the specific, narrower rules the Greeks themselves had set for a construction to count. Straight edge and compass, nothing else. And for roughly 2,000 years, the assumption remained that some cleverer construction, obeying those exact rules, was still out there, simply waiting to be stumbled onto. As one modern account of the problem puts it plainly, the ancient Greeks believed the construction problems they could not solve were just stubborn, not actually unsolvable. They were wrong about that, and it took until the 1800s to find out how wrong. Ironically, the first real crack in the problem was a success rather than a failure. In 1796, a 19-year-old Carl Friedrich Gauss showed that a regular polygon with 17 sides, a heptadecagon, could be constructed using nothing but straight edge and compass, something nobody had managed for a shape that oddly specific before. 5 years later, in his book Disquisitiones Arithmeticae, Gauss went further and gave a full, sufficient condition for exactly which regular polygons are constructible at all, a condition built around a special family of prime numbers called Fermat primes. Gauss believed his condition was also necessary, though he never actually proved that half of it. The mathematician who closed every remaining piece of this puzzle at once was Pierre Wansel in 1837. Wansel proved that Gauss's condition for constructible polygons was indeed necessary as well as sufficient, finishing that specific question completely. And in the very same paper, using the same underlying method, Wansel proved that trisecting an arbitrary angle and doubling the volume of a cube are both flatly impossible with straightedge and compass alone, for any angle or cube where the construction isn't already trivial. The actual list of constructible regular polygons, once Gauss and Wansel had fully pinned it down between them, starts 3, 4, 5, 6, 8, 10, 12, 15, 16, 17, 20, and keeps climbing from there in a pattern that looks close to random on first glance, but is completely determined by that same rule about Fermat primes underneath it. A regular seven-sided polygon can't be built this way. Neither can 9, 11, 13, or 14 sides. There are only 5 Fermat primes currently known to exist at all, and nobody knows whether there are more of them still waiting to be found, or whether 5 is the entire list forever, which means nobody currently knows the complete list of constructible regular polygons either. Only the rule for generating it once the underlying question about Fermat primes gets settled, if it ever does. Squaring the circle held out a little longer, until 1882, when Ferdinand von Lindemann proved that the number pi is transcendental, meaning it can be the root of any polynomial equation with rational coefficients at all, no matter how high the degree, since squaring the circle requires constructing a length equal to the square root of pi. And pi isn't even the kind of number that straightedge and compass constructions can ever reach, that settled the last of the 3 ancient problems for good, the reason all 3 fall the same way, and the reason it connects so cleanly to everything already covered is close to elegant. Every point constructible with a straight edge and compass, starting from a couple of given reference points, turns out to correspond to a number reachable using only addition, subtraction, multiplication, division, and square roots, nothing else, no cube roots, no higher roots, ever. That's it. That's the entire toolbox straightedge and compass constructions have access to, translated into algebra. Every square root taken in the course of a construction corresponds to climbing one more step up a tower of field extensions, each new step exactly doubling the size of the field currently being worked inside, which means any number reachable by straightedge and compass has to sit at the top of a tower built entirely out of doublings, and the degree of that number, the size of the smallest polynomial with rational coefficients that has it as a root has to be some power of 2, no exceptions. Every straight edge in compass construction, no matter how elaborate, reduces down to just 5 basic moves, repeated over and over, drawing a line through 2 existing points, drawing a circle centered at one existing point, and passing through another, and marking the new points created wherever 2 lines, 2 circles, or a line and a circle happen to cross. Nothing else is allowed ever, and everything the ancient Greeks managed to build, equilateral triangles, squares, regular pentagons, angle bisectors, perpendicular lines, came from nothing more than chaining those 5 moves together in longer and longer sequences. Turning geometry into algebra this way, treating points and lines as symbols, and treating a construction as an algorithm acting on those symbols, was, by most accounts, first fully realized by Gauss himself. And it's the same realization that let him prove some constructions impossible well before one so finished the job. It also cuts the other direction, letting a construction get proven possible without a single line necessarily needing to be drawn first. Knowing that the cosine of the relevant angle sits at the top of a tower of square root extensions is, by itself, already enough to guarantee the 17-sided polygon is constructible, well before anyone works out the specific sequence of circles and lines needed to actually draw it. It would take until David Hilbert, decades later, to work out a complete, fully rigorous set of starting axioms for geometry itself, closing a gap that had technically been sitting open since Euclid's own Elements, for all its rigor, had leaned on unstated visual assumptions in a handful of its proofs, gaps nobody had thought to formalize because the diagrams themselves always seemed to settle the matter well enough for 2,000 years of readers. That single fact kills all 3 ancient problems in one stroke, 3 separate geometric puzzles that spent 2,000 years looking like they might have 3 separate answers, or no answer at all, finally reveal as 3 faces of one and the same algebraic obstruction. Doubling the cube requires constructing the cube root of 2, and the cube root of 2 has degree 3 over the rational numbers, since its minimal polynomial is x cubed minus 2. And 3 isn't the power of 2, not 4, not 8, nothing in that family. Trisecting a generic 60-degree angle, to pick one concrete case, requires constructing the cosine of 20 degrees. And that number also turns out to have degree 3 for the same reason, not a power of 2. And squaring the circle needs the square root of pi, which isn't even algebraic at all, degree infinite in a sense, so it was never within reach to begin with. None of these are failures of cleverness, and no future mathematician, however brilliant, patient, or well-funded, will ever stumble onto a construction that gets around them the same kind of permanence already established for the quintic formula earlier in this tour, just reached this time through geometry rather than through an equation's roots. They are the direct algebraic consequence of a toolbox that only ever allows doubling, never tripling, of the field currently being stood on. It's worth being exact about what did and did not get closed off here, because the boundary is exactly as sharp as it sounds, and not one bit sharper. None of this means trisecting an angle is impossible in some final, absolute sense for every tool anyone could ever dream up. It means it is impossible with exactly those two tools and no others. And that narrower, sharper claim has never once needed revisiting since 1837. A whole side industry of geometric problems has been mapped out using this same method since then, well past the three ancient headline cases. Pick any three notable points belonging to a triangle out of a list of 16 candidates, its corners, the midpoints of its sides, the feet of its altitudes, its center of mass, and so on. And there turn out to be 139 distinct problems buried in just picking three of those points and trying to reconstruct the whole triangle from them. Only 74 of those 139 are constructible with an ordinary straight edge and compass in the general case. 23 more work only under special extra conditions, and 39 of them, even though a triangle satisfying the conditions definitely exists, can never be built with straight edge and compass, no matter how cleverly someone tries. Even something as concrete sounding as a billiard problem, reflecting a ray of light off a curved spherical mirror to hit a specific target, first posed by the mathematician Alhazen roughly 1,000 years ago, was not proven impossible by straight edge and compass alone until 1997, when the Oxford mathematician Peter Neumann finally closed it out using the same field extension logic that had already closed everything else. The boundary really is precise rather than fuzzy, and it responds in an exact, predictable way to handing a mathematician one extra tool. A straight edge with two fixed marks scratched onto it instead of a bare, unmarked edge is enough on its own to trisect any angle and double any cube, a technique called neusis that the ancient Greek mathematicians Archimedes and Nicomedes both worked out methods for. That single addition, two marks, unlocks cube roots, much like a bare compass, and straight edge unlock only square roots. And once cube roots are available, degree, three problems that were flatly impossible a moment ago become completely routine. Paper folding turns out to be more powerful again. The formal rules of origami construction, laid out as the Husita-Hattori axioms, can solve cubic and even quartic equations directly through a sequence of folds, which is part of why some regular polygons that can be folded cleanly out of paper still can be built with an unmarked straight edge and compass. None of this weakens Wansel's proof by so much as an inch. It sharpens it into something closer to a dial than a wall. Exactly two tools closes exactly this many doors. Add one mark to the ruler, and a specific, predictable, provable set of new doors swings back open. So there it is, twice now, in two completely different parts of mathematics, equations, and geometry, the exact same shape of impossibility. Not a hard problem, still waiting on the right idea. A door that has been proven, using algebra both times, to have no other side. It's worth pointing out what a strange kind of proof this even is, since it runs backward from how proving something impossible usually works. Most of the time, proving a task can't be done means checking every single attempt and watching each one fail, which is hopeless the moment infinitely many attempts are possible. And trisecting an angle allows for infinitely many possible constructions, infinitely many combinations of circles and lines drawn in whatever order a person likes. Wansel's proof never checks a single one of those attempts directly. It steps outside the geometry entirely, translates the whole problem into a question about the algebraic degree of a number, and answers that translated question instead, a question with only a small handful of possible answers instead of infinitely many. That's the real trick both times, geometry and equations alike. Translate an infinite haystack of possible attempts into one small, finite algebra problem, and let the algebra settle it once and for all. Two closed doors covered now, one built from equations, one built from geometry, and they looked completely different walking in, then turned out to be identical walking out. Nobody setting out to trisect an angle with a compass expected the answer to hinge on whether a number's degree happened to be a power of 2. Nobody chasing a quintic formula expected the answer to hinge on whether a particular group of shuffles could be broken into small enough pieces, an object nobody involved in the earliest attempts even had a name for yet. Both searches ran for centuries before anyone found the actual key, and in both cases, the key turned out to live in a place nobody involved was originally even looking. A completely different branch of mathematics smuggled in through the back door to answer a question the front door never could. Algebra, then, has a small collection of permanently closed doors. But the objects algebra actually works with, the things allowed to be plugged into those equations in the first place, turn out to be strange in an entirely different way. And the strangeness starts with a number that got handed an insult for a name and never once got a better one. Every complex number is written in the form a plus b I, where a and b are ordinary real numbers, and I stands for a special quantity whose square equals -1, something no real number can do, since squaring any real number, positive or negative, always lands back on a positive result. That single rule, I squared equals -1, is the entire foundation the rest of the system is built on. Historically, it shows up first as an unwanted side effect of solving cubic equations, not quadratics. Gerolamo Cardano ran into square roots of negative numbers around 1545 while working through his cubic formula, and he did not like what he found. He described using them as a kind of mental torture, and later called the whole idea, as subtle as it was, useless. Cardano used them anyway, because the arithmetic demanded it, but he clearly wished he did not have to. The mathematician who actually worked out real rules for handling them, addition, subtraction, multiplication, root extraction, was the Italian Raphael Bombelli, wrestling with a specific and strange situation mathematicians call the irreducible case. Take a cubic equation where all three roots are perfectly ordinary, real numbers. Nothing imaginary about the answer at all, and hand it to Cardano's formula anyway. The formula still forces a detour through a square root of a negative number somewhere in the middle of the calculation, even though it's guaranteed to land back on a plain real number by the end. There is no way to dodge it by factoring differently either, if the cubic can't be broken into smaller pieces first. Bombelli was the one who sat down and actually figured out how to carry that detour through negative square roots and come out the other side with the correct, real answer waiting. The name imaginary itself came from René Descartes in 1637, and his own writing on the subject makes the dismissiveness explicit instead of incidental, describing these numbers as ones a person can always imagine as many of as an equation seems to call for, even in cases where nothing in the real world actually corresponds to what's being imagined. That's not a neutral technical description. It's a polite way of saying the numbers are a bookkeeping fiction useful for finishing a calculation, but not to be trusted as describing anything real. The label stuck immediately, and it never once got swapped out for something less loaded, even centuries after mathematicians had stopped doubting these numbers were legitimate in any meaningful sense. Compare that to how mathematics usually handles an outdated name. Negative numbers, covered earlier, stopped being called absurd the moment the objection died out. The insult simply fell out of use once nobody meant it seriously anymore, and the label Chuquet and Stifel both reached for never calcified into anything permanent. Imaginary numbers took the opposite path entirely. The insult didn't fall out of use. It got promoted into the official, permanent textbook term for the entire number system, printed on the cover of courses taught to teenagers who have never once doubted these numbers exist. Leonhard Euler, one of the most productive mathematicians who ever lived, still tripped over them regularly, an identity that works perfectly for ordinary positive numbers. The square root of a times the square root of b equals the square root of a times b breaks down the moment both a and b are negative, and getting that distinction wrong caused real errors. For Euler, among others, for a long stretch of the 16 and 1700s. That kind of slip is a humbling detail to sit with, given who was making it. Euler is routinely counted among the small handful of the most prolific and reliable mathematicians who ever lived. And even he needed a special symbol invented, the letter I standing in for the square root of -1, specifically to stop himself and everyone reading his work from accidentally sliding back into that exact mistake. It took until 1831 for the picture to really settle. Carl Friedrich Gauss, who had already been using complex numbers with real confidence since well before that, finally published his treatise treating them as points on a plane, establishing much of the modern notation and terminology in the process. Gauss introduced the letter I for the square root of -1 and coined the actual term complex number. He also left behind a line about the whole naming mess that is hard to improve on. If earlier mathematicians had not called +1, -1, and the square root of -1 positive, negative, and imaginary, but had instead called them something like direct, inverse, and lateral, there would hardly have been any of that mysterious darkness people kept describing around the subject. The mathematician Caspar Wessel had actually described the same complex plane idea back in 1799 in a paper that went almost completely unnoticed at the time, and Jean-Robert Argand independently published a similar picture in 1806, along with the first fully rigorous proof of the fundamental theorem of algebra. None of that history changes what a complex number actually does mechanically. It behaves exactly like an ordered pair of real numbers, a real part and an imaginary part, added and subtracted the obvious way, part by part. Multiplication is where the I squared equals -1 rule earns its keep, since multiplying two complex numbers together and simplifying using that one substitution rule produces another complex number, following a clean and completely mechanical formula. Every non-zero complex number has a multiplicative inverse too, which means division works for any complex number except 0. And division still always produces another complex number. No exceptions, no getting kicked out of the system. Run one plain example to see the mechanics up close. Multiply the quantity 2 plus 3i by the quantity 1 minus 4i, and distributing it out the same way any two binomials get multiplied gives 2 times 1 plus 2 times -4i plus 3i times 1 plus 3i times -4i. That's 2 minus 8i plus 3i minus 12i squared. Substitute -1 in for that final I squared, since that's the entire rule the whole number system is built on. And -12 times -1 becomes +12. Combine the plain numbers, 2 plus 12, and combine the I terms, -8i plus 3i, and the whole thing collapses down to 14 minus 5i, one single ordinary complex number. Exactly the shape every complex number is guaranteed to keep no matter how many of them get multiplied together. That combination, addition, subtraction, multiplication, and division, all staying inside the same closed system, is exactly what makes the complex numbers a field in the same technical sense. The rational numbers and real numbers are fields, a fact that will matter a great deal later on. The part almost nobody expects, coming from a name built on an insult, is how load-bearing these numbers turned out to be everywhere once engineers and physicists got their hands on them. Electrical engineers analyzing an alternating current circuit fold resistors, capacitors, and inductors into a single complex number called impedance. And the entire mechanical process of solving circuits gets dramatically simpler once that combined complex form is allowed to replace tracking sines and cosines separately. Engineers in that field use the letter J instead of I for the imaginary unit specifically because I is already taken for electric current. Control theory, the branch of engineering that figures out whether a bridge, an airplane, or a thermostat will settle down or oscillate wildly out of control, plots a system's behavior as points in the complex plane and reads off stability directly from which half of that plane those points land in, a direct practical descendant of the same discriminant sign check already covered back when the quadratic formula first split its answers into real and complex cases. Land on the left half of the plane, real part negative, and the system settles down over time, calming toward equilibrium the way a struck bell eventually falls quiet. Land on the right half instead, real part positive, and the system runs away from itself, oscillations growing larger and larger instead of dying out, the mathematical signature of an engineering failure waiting to happen. Land exactly on the dividing line between the two halves, and the system sits at the edge, neither settling nor blowing up, a razor-thin boundary condition engineers spend a great deal of design effort staying well clear of. Quantum mechanics is arguably the deepest dependency of all. The Schrödinger equation, the equation that governs how a quantum system evolves over time, is written directly in terms of complex numbers, and the wave functions that describe where a particle probably is are complex valued functions living in something called a complex Hilbert space, not a mathematical convenience layered on top of the physics, but part of the actual physics itself. Signal processing, digital audio, digital image compression, Fourier analysis generally, all lean on complex numbers to describe waves cleanly, since a real valued wave, a sound or a radio signal, can be written as the real part of a rotating complex number, and rotating complex numbers are far easier to add, multiply, and shift in time than raw sines and cosines ever were. Even the two-dimensional fluid flow equations used in fluid dynamics get folded into complex function theory. The Mandelbrot set, one of the most recognizable images to ever come out of mathematics, is nothing more than repeatedly squaring a complex number and adding a constant back in, over and over, and watching which starting points blow up and which ones stay bounded forever. A whole intricate, endlessly detailed picture, the kind that keeps revealing new structure the further anyone zooms into its edge, falls straight out of a rule simple enough to state in one sentence, purely because the rule happens to be running on complex numbers instead of plain, real ones, where the same simple rule produces nothing nearly as rich. There's a clean piece of algebraic number theory that falls out of all this too, one with a very concrete geometric punchline. Field theory, built directly on top of complex numbers, can be used to prove that a regular nine-sided polygon, a nonagon, can't be constructed with straight edge and compass. The exact same kind of impossibility already covered, reached this time by a completely different route, through the numbers themselves, rather than through field extension towers built from square roots alone. That's an odd loop to notice. A number system born out of embarrassment over negative square roots, insulted by name for 100 years, ends up supplying one of the cleanest available routes to proving an ancient Greek geometry problem impossible, a problem that has nothing to do with negative numbers, square roots, or anything imaginary sounding on its face. There's a second, completely independent way to represent a complex number, one that has nothing to do with plotting a point on a plane, and it turns out to fold complex numbers directly into a piece of algebra covered later in this tour. Any complex number, a plus b, I can be written instead as a small 2 by 2 grid of ordinary real numbers, with a sitting in the top left and bottom right corners, and b and its negative sitting in the other two corners. Add or multiply two of these grids using the ordinary rules for combining grids of numbers, and the result matches step for step exactly what happens when the original complex numbers are added or multiplied the usual way. A complex number and a specific small grid of real numbers turn out to be two outfits worn by the same underlying object. Complex numbers show up in plane geometry too, in places that look like they should have nothing to do with imaginary numbers at all. Every triangle contains a unique ellipse called its Steiner inellipse that sits tucked inside the triangle and just touches the midpoint of each of its three sides. Plot the triangle's three corners as complex numbers. Build the cubic equation with exactly those three complex numbers as its roots take its derivative, and the two roots of that derivative, generally complex numbers themselves instead of real ones, mark the exact two focus points of that hidden ellipse. That fact has a name, Marden's theorem, and it is a purely geometric statement about triangles and ellipses that happens to have no clean proof at all without stepping through the complex plane along the way. William Rowan Hamilton pushed the whole idea one step further than Gauss did. And the process he used has a name worth knowing: the Cayley-Dixon construction, a recipe for doubling a number system's dimension over and over, each time trading away one comfortable property to gain more room, starting from the real numbers. And running the recipe once produces the complex numbers, trading away the number lines built in sense of order, whether one number is bigger than another. For the extra room to solve equations like x squared plus 1 equals 0, Hamilton ran the recipe a second time in 1843 and produced the quaternions, a four-dimensional number system. And this time, the price was steeper. Quaternion multiplication stops commuting entirely. A, B no longer generally equals B, A. Run the recipe once more, and the result is the octonions, an eight-dimensional system that gives up even more, associative multiplication itself, so that grouping three octonions differently can change the answer. Keep running the recipe past that point, and the whole system eventually stops being useful for much of anything, since each doubling trades away real structure for real room. And there's only so much structure left to trade. There's a tidy way to pin down exactly what makes the complex numbers, separate from any of the history around them. And it comes down to just three properties. First, adding the number 1 to itself over and over, no matter how many times, never once lands back on 0, a property called having characteristic 0, which the complex numbers share with the rational and real numbers, but not with clock arithmetic built on a prime-sized clock. Second, the complex numbers are, in a precise technical sense, exactly as large an infinity as the real number line itself, no bigger and no smaller, despite feeling like they ought to be a whole extra dimension's worth of numbers. And third, the property already covered at length, being algebraically closed. Every polynomial equation gets a root. Any number system, anywhere, that happens to satisfy all three of those properties at once turns out to be structurally the exact same thing as the complex numbers, no matter how differently it might have been built or what it might be called. There's a more visual, less algebraic fingerprint too, one that separates the complex numbers from the real numbers instantly, without needing any of the three technical properties at all. Remove 0 from the real number line, and it falls apart into two separate pieces. Everything positive sitting on one side, everything negative on the other, with no way to walk from one piece to the other without passing back through 0. Remove 0 from the complex plane instead, and nothing similar happens at all. The remaining points stay one single connected sheet, since there's always a path curving around the missing origin from any non-zero complex number to any other one. That single difference, falling apart into two pieces versus staying in one connected piece, is enough on its own to prove the real numbers, and the complex numbers can never be the exact same kind of structure. No algebra required, just the shape of the two spaces themselves. There's even a strange consequence sitting inside that fact, that the complex numbers contain smaller copies of themselves tucked inside, proper subfields that are, on their own, isomorphic to the entire complex number system they're sitting inside of, infinitely nested, each full copy fitting inside a slightly larger version of itself. So, the numbers picked up an insult for a name in the 1500s on the strength of a handful of mathematicians who found them baffling and said so. And mathematics simply never got around to renaming them, even after they turned out to be one of the most useful and structurally important inventions in the entire subject. Imaginary was never a fair description. It just stuck. Once complex numbers are allowed into the picture, something else falls into place, something with a name so grand it promises far more than it delivers. The fundamental theorem of algebra states that every polynomial equation of degree n with complex number coefficients has exactly n complex roots. Counting any repeats, a degree 2 equation has exactly 2 roots. A degree 5 equation has exactly 5. A degree 100 equation has exactly 100. No exceptions, ever, as long as complex numbers are on the table. The name oversells it a little, and the mathematics itself more or less admits as much. Despite being called fundamental, the theorem isn't actually fundamental to how modern algebra is organized. And the name is really a leftover from a much older era, back when algebra as a word simply meant the theory of equations, solving for x full stop. There's an even stranger wrinkle sitting right underneath the name. The fundamental theorem of algebra can't be proven using only algebra. Every known proof needs to borrow tools from outside the field entirely, from analysis, the branch of math built on limits and continuity, or from topology, the branch built on stretching and bending shapes without tearing them. A theorem named after algebra that algebra alone can't prove. Getting to a fully correct proof took roughly 200 years and passed through the hands of most of the biggest names in the field, each attempt leaving something unfinished behind for the next person. Peter Roth in 1608 and Albert Gerard in 1629 both floated the idea that a degree and equation should have n solutions, without insisting those solutions be real numbers, though neither one had anything close to a proof. Gerard worked through an actual example to make his case. The equation x to the fourth equals 4x minus 3, which he showed has exactly 4 solutions once repeats, and complex numbers both get counted properly. 1 repeated twice over, plus a pair of complex conjugates, -1 plus the square root of -2, and -1 minus the square root of -2. Jean Laurent d'Alembert made the first real attempt at an actual proof in 1746, and it was incomplete, leaning on another result that itself would not be proven for more than a century. Euler, de Foncenex, Lagrange, and Laplace each took a swing at it later in the 1700s, and every one of them assumed the very thing that needed proving, that a full set of roots existed somewhere for the equation to have in the first place. Gauss produced a mostly geometric proof in 1799 that still had a hole in it, a topological gap nobody managed to fully patch until Alexander Ostrowski did it in 1920, more than 100 years later. The first proof that actually held up all the way through came from Jean-Robert Argand, an amateur mathematician working outside the professional establishment entirely in 1806, later revisited in 1813. It was also the first version of the theorem stated for complex coefficients generally, instead of just real ones. The first time a proof of the theorem appeared inside an actual published textbook was Augustin Louis Cauchy's book in 1821, and Cauchy used Argand's proof to do it without crediting Argand for it. Gauss himself was not done either, producing two more proofs later in his life, in 1816, and again in an incomplete revisiting of his own original approach in 1849. Karl Weierstrass, in the middle of the 1800s, raised an entirely different question, whether a proof could be made constructive, meaning it would not just show that roots exist, but actually hand over a method for finding them. And he published his own answer to that in 1891. The search for cleaner proofs never really stopped either. Even now, modern textbooks still turn up fresh angles of attack. One popular linear algebra textbook builds a proof entirely out of de Moivre's formula, the same tool already used to compute powers of complex numbers, combined with a basic fact from calculus about functions on a bounded region, always reaching a minimum somewhere. A theorem 200 years settled still gets reproven periodically by people looking for a shorter or more elegant road to the same destination. That habit isn't wasted effort either. A shorter proof often carries a clearer explanation of why a theorem is true buried inside it, and a proof built out of tools from a completely different branch of mathematics, analysis instead of topology, calculus instead of geometry, tends to reveal connections between fields that the original proof, built with whatever tools happened to be on hand at the time, never had any reason to expose. The fundamental theorem of algebra has, by this point, been proven using nearly every major branch of mathematics that existed by the middle of the 20th century: complex analysis, topology, algebra itself, and even a version built on Riemannian geometry, each proof a different lens on the exact same underlying fact. Every one of those early failed attempts shares the same shape of mistake, worth naming plainly, because it's such a natural mistake to make. Each mathematician kept assuming that a full set of roots already existed somewhere out there waiting to be described, and then spent all their actual effort working out what those already assumed roots had to look like. That's backward. The hard part of the whole theorem was never describing what the roots would look like if they existed. It was proving that even one of them has to exist at all, starting from nothing but the bare polynomial, with no roots handed over for free at the start. It is the exact same trap Ruffini fell into while trying to prove the quintic unsolvable decades earlier, assuming his radical expressions had to be built entirely out of the equation's own roots, a trap only fully sprung and identified once Abel came along and refused to take that particular shortcut. Once a mathematician stops assuming the conclusion and actually earns it, the proof gets dramatically harder. And that difference in difficulty is exactly why it took 2 centuries, several of the biggest names in the entire history of mathematics, and, in the end, an outsider working completely outside the professional establishment to finally close the gap. What the theorem actually buys, once it's finally nailed down, is bigger than the count of roots by itself. There is an equivalent, entirely real number way to state the whole fundamental theorem too, one that never once has to mention a complex number by name, useful for anyone who wants the guarantee without the machinery. Every real number polynomial of degree higher than 2, no matter how high that degree climbs, can be factored down into a product built entirely out of pieces of degree 1 and degree 2, straightforward linear factors and simple quadratic factors, and nothing more complicated than that is ever required. Once complex numbers are allowed as an intermediate step, even if every starting coefficient was a plain, real number. Even Gottfried Leibniz got caught out by this exact guarantee. In 1702, he flatly claimed that a polynomial shaped like x to the fourth plus a fourth for some real number a could never be broken down into smaller real factors at all. A few decades later, the mathematician Nicolaus Bernoulli made the same kind of claim about a different specific polynomial, x to the fourth minus 4x cubed plus 2x squared plus 4x plus 4, and sent it to Leonhard Euler as an example he assumed had no clean factorization. Euler wrote back in 1742 with the actual factorization spelled out: 2 real quadratic pieces multiplying together to give exactly that polynomial, proving both Leibniz and Bernoulli wrong about their own specific examples. Leibniz had run into a genuine edge case where the intuition trained by simpler polynomials broke down and mistook a personal blind spot for a hole in the mathematics itself. And any root that isn't itself a real number always shows up paired with its mirror image, its complex conjugate. So the count of non-real roots in a real polynomial is always an even number, never odd. That pairing is the direct descendant of the discriminant wrinkle from the quadratic formula section, the one asked to be held onto earlier. A negative discriminant doesn't mean a quadratic equation has no solutions. It means the 2 solutions have stepped off the real number line and onto the complex plane, still exactly 2 of them, still paired as mirror images of each other, exactly as the fundamental theorem promises they must be. One of the more visual proofs of the whole theorem, the kind that can be pictured instead of just calculated, comes from watching what a polynomial does to a big loop. Take any polynomial and feed it every point sitting on a large circle in the complex plane, tracing that circle all the way around once. Feed the results back out and plot them. and they trace their own loop, a closed path that winds around the very center of the plane, the origin, some whole number of times before closing up. For a circle large enough, the highest degree term in the polynomial completely swamps every smaller term. So the output loop ends up winding around the origin exactly as many times as the polynomial's degree, no matter what the smaller terms are doing. Now shrink that circle down, step by step, all the way to a single point sitting at zero. If the polynomial never touched zero anywhere in the whole plane, that winding count would somehow have to smoothly change from the polynomial's degree out at the white circle down to zero at the shrunken point, without ever passing through a moment where the loop crosses directly over the origin itself, which is a contradiction, since winding counts only change at the instant a loop crosses the exact point being wound around. Something has to give, and what gives is the assumption that the polynomial never touches zero. It has to, somewhere inside that shrinking circle, and that's a root. There's a related bound worth knowing about too, since it turns the fundamental theorem from a pure existence statement into something closer to a practical tool. Given the coefficients of a polynomial, a rough circle can be drawn in the complex plane, sized directly from those coefficients, that's guaranteed to contain every single root, with none escaping outside it. That doesn't hand over the roots themselves, but it narrows the search from the entire infinite plane down to one specific calculable region, and pairing that bound with the fundamental theorem's guarantee that the roots exist somewhere inside is exactly what makes modern numerical root finding algorithms work reliably at all. Being algebraically closed, the exact technical name for what the fundamental theorem hands the complex numbers, isn't a property every number system gets to have. The rational numbers are not algebraically closed, since x squared minus 2 has no rational root at all, the square root of 2 being famously irrational. The real numbers are not algebraically closed either, since x squared plus 4 has no real root, nothing that squares back to negative 4. The complex numbers are the smallest number system built on top of the real numbers that finally closes that gap completely, guaranteeing a root for absolutely everything. And that is the specific sense in which the complex numbers count as complete, in a way the rational and real numbers never quite managed to be. The theorem also turned out to be a single variable warm-up act for a much bigger question: what happens once a polynomial gets more than one variable at a time? Hilbert's Nullstellensatz, German for a theorem about the locations of zeros, is the multivariable generalization of the exact same idea, connecting the algebra of a system of polynomial equations directly to the geometry of the shapes those equations describe, and it sits at the very foundation of an entire field called algebraic geometry. Bezout's theorem does something similar for counting purposes, predicting exactly how many points two curves described by polynomial equations ought to cross at once every intersection gets counted properly, including the ones that only show up once. Complex numbers, instead of just real ones, are allowed into the picture. The same generosity that made the one variable version of the fundamental theorem work in the first place. Matrix multiplication is where a lot of people first meet a rule in algebra that flatly contradicts something they've trusted since they were 7 years old. That multiplying two things together gives the same answer, no matter which order the multiplication happens in. 3 times 5 and 5 times 3 have always been the same number. That's just how multiplication works. In every single arithmetic class from kindergarten forward, matrices break it on purpose, and the break isn't a bug hiding somewhere in the notation. It's the entire point. A matrix is a rectangular grid of numbers, and matrix multiplication was introduced by the French mathematician Jacques-Philippe Marie Binet in 1812, specifically to represent the combined effect of applying one transformation and then another. The actual mechanical recipe for multiplying two matrices: take a row from the first one, take a column from the second one, multiply matching entries together, and add up the results, is taught as exactly that, a recipe. Something to follow step by step without necessarily asking what it means. Most students memorize the recipe and move on. The part that tends to get skipped is sitting with why the recipe behaves the way it does once it actually gets run both directions. Here is the simplest possible version of the problem. Take two small 2 by 2 matrices. The first one has a 1 in the top right corner and zeros everywhere else. The second one has a 1 in the bottom left corner and zeros everywhere else. Multiply the first one by the second one in that order, and the result is a matrix with a single one sitting in the top left corner. Now multiply them again, same two matrices, opposite order, second one times first one, and the result this time has its lone one sitting in the bottom right corner instead. Same two matrices. Same operation. Reverse the order, and the answer lands in a literally different corner of the grid. Swap in ordinary, less extreme numbers, and the same disagreement still shows up, just less dramatically. Multiply the 2 by 2 matrix with rows 1, 2, and 3, 4 against the 2 by 2 matrix with rows 0, 1, and 1, 0. In that order, and the result comes out as rows 2, 1, and 4, 3. Multiply those exact same two matrices in the reverse order, and the result comes out as rows 2, 4, and 1, 2 instead. The two rows swapped from top to bottom instead of left to right. A different final grid built from the identical starting ingredients. It's tempting to write that off as some kind of quirky edge case, two specially chosen matrices that just happen to clash, the way a handful of oddly shaped numbers can trip up an otherwise reliable rule of thumb elsewhere in math. It isn't an edge case here. Pick two matrices, completely at random, of any size, with any numbers at all filled in, and the two possible orders almost never agree. Not occasionally, not usually, essentially never. Commuting is the rare exception among matrices, not the norm, which is exactly backward from how every other kind of multiplication a person meets before algebra class behaves. That's not a subtle difference buried in decimal points somewhere. It's a completely different matrix with the one in a different spot every time. The reason this happens, and the reason it's the expected outcome instead of some kind of glitch, comes from what matrices actually represent. A matrix is a stand-in for a transformation, a rule that takes one set of numbers and turns it into a different set of numbers, a rotation of a shape in space, a scaling, a reflection, or, in a completely different context, a table describing how many units of raw material get consumed to build 1 unit of some intermediate product. Multiplying two matrices together is the same operation as doing one transformation and then doing the other one. First this rule, then that rule. And doing two transformations in one order is frequently just a different transformation than doing them in the other order. The same way, putting on socks and then shoes leads somewhere different than putting on shoes and then trying to put socks on over them. Function composition, applying one function and then applying a second one to the result, has never generally been an order-independent operation. And matrix multiplication is function composition wearing a grid of numbers as a disguise. There's a case where multiplication does still commute cleanly, and it's worth naming because it sharpens the general rule rather than undercutting it. Rotating a shape around a fixed center by some angle, and then rotating it again by a second angle, gives the exact same final result, no matter which rotation gets applied first, since rotating by one angle and then a second angle around the same point always comes out as one combined rotation by the sum of the two angles, regardless of order. Two rotations around the same center do commute. The matrix for rotating by some angle is built out of that angle's sine and cosine, arranged in a small 2x2 grid, and multiplying the rotate by one angle matrix against the rotate by a second angle matrix, worked all the way through using the ordinary trigonometric identities for the sine and cosine of an added angle, collapses back down into a single rotation by the sum of the two angles. No matter which of the two rotations gets applied first, since adding two angles together obviously doesn't care what order the addition happens in. What generally doesn't commute is mixing different kinds of transformations together, a rotation combined with a stretch along one axis, say, or two rotations happening around two different centers rather than the same one. The rule that multiplication commutes turns out to be the exception in this world, reserved for very specific matching pairs, like two matrices that are both diagonal, meaning every non-zero entry sits on the same straight line through the grid, or one of the matrices being a plain scalar multiple of the identity matrix, the matrix version of the number 1. Outside those special cases, order matters, full stop, and there's no getting around it by picking friendlier numbers. There is at least one comfort buried in all of this, and it's associativity, which survives even though commutativity doesn't. Multiplying three matrices together, A times B times C, gives the same final answer, whether A times B gets computed first and then multiplied by C, or B times C gets computed first with A multiplied into that. The answer doesn't change based on how the multiplications get grouped, only based on what order the matrices get written in from left to right in the first place. That distinction turns out to matter for a reason that has nothing to do with correctness and everything to do with speed. The actual arithmetic behind that gap is worth walking through once, since it explains why the difference is as large as it is, rather than just asserting it. Multiplying a 10 by 30 matrix against a 30 by 5 matrix first costs 10 times 30 times 5, multiplications 1,500, producing a 10 by 5 result. And then multiplying that 10 by 5 result against the 5 by 60 matrix costs 10 times 5 times 60 more, 3,000, for a running total of 4,500 individual multiplications. Grouping the last two together first instead, before bringing in the first one, takes about 27,000 multiplications for the exact same final answer. Same three matrices, same order, left to right, same correct result either way, and a six-fold difference in how much arithmetic it costs to get there, depending purely on which pair gets multiplied first. Multiplying two ordinary n by n matrices together, using the straightforward row times column recipe everyone learns first, costs roughly n cubed individual multiplications. And for a long time, that was assumed to be about as good as it could get. It wasn't. In 1969, Volker Strassen found a faster method, cutting the cost down to roughly n raised to the power of 2.8 instead of 3, by finding a cleverer way to combine fewer multiplications with more additions. The record has kept falling since. As of January of 2024, the best-known method, developed by Virginia Vasilevska Williams, Yinjian Xu, Zixuan Xu, and Renfei Zhou, gets the exponent down to roughly 2.37. Nobody knows whether matrix multiplication can ever be pushed all the way down to something close to n squared, which would be the theoretical floor, since every entry in both matrices has to be read at least once, no matter what method gets used. Every advance since Strassen has shaved the exponent down by smaller and smaller amounts, and each new record has typically taken years of specialized research to uncover, a sign that whatever headroom is left between the current best exponent and the theoretical floor of 2 is being fought over in increasingly small increments, rather than in the kind of large leap Strassen himself first made. That question is still sitting open, more than half a century after Strassen first showed the obvious method wasn't the best one. Matrices earn their keep well past pure abstraction too, and one plain economics example makes that concrete fast. Picture a small factory that turns 4 kinds of raw materials into 3 kinds of intermediate parts, and those 3 intermediate parts then combine to build 3 kinds of finished products. The recipe connecting raw materials to intermediate parts is just a grid of numbers. So many units of material, 1 needed per part 1. So many units of material, 2 needed per part 2, and so on. And the recipe connecting intermediate parts to finished products is a second grid built the same route. Multiply those 2 grids together in the right order, and the single combined grid that pops out tells the factory manager exactly how many units of each raw material get consumed per finished product, with every intermediate step already folded invisibly into the arithmetic. Nobody has to manually trace a bolt through two separate stages of production to know how many bolts a finished product actually needs. The matrix multiplication already did the tracing. There's one number attached to a square matrix that decides by itself whether the matrix can even be undone, called the determinant. And it turns out to interact cleanly with all of this, despite everything else about matrices, refusing to behave politely. Even though A times B essentially never equals B times A, the determinant of A times B always equals the determinant of B times A, both of which equal the determinant of A multiplied by the determinant of B, a small island of order sitting in the middle of an operation that otherwise cares deeply about sequence. A matrix's determinant coming out to exactly zero is the single cleanest signal that the transformation it represents collapses space down somehow, flattening a whole plane onto a single line, say, and losing information permanently in the process, information no inverse operation can ever get back. Matrices also come with their own quiet echo of an idea that showed up already, back with the quadratic formula's discriminant. Feed a square matrix into a transformation and ask whether there's some direction the transformation leaves fundamentally alone, stretching or shrinking a vector without rotating it off its own line entirely. A vector doing exactly that is called an eigenvector, and the amount it gets stretched or shrunk by is its eigenvalue, a pair of German-derived terms. Eigen meaning something close to own or characteristic, that have simply stuck in English mathematical vocabulary rather than ever getting fully translated, and finding those eigenvalues comes down to solving a plain polynomial equation built out of the matrix's own entries. For a large matrix, that can mean solving an equation of very high degree indeed, which ropes eigenvalue problems straight back into everything already covered, about which equations even have a formula to find their roots with in the first place. There's a related trick called a similarity transformation that lets a messy-looking matrix get swapped out for a cleaner one describing the exact same underlying transformation, just viewed from a more convenient angle, the mathematical version of rotating a photograph until whatever's being looked at finally sits upright. Every property that actually matters about the transformation itself, its eigenvalues among them, survives that swap completely untouched, even though the grid of numbers representing it looks nothing alike before and after. Polynomials keep showing up as a hidden bookkeeping device, well outside pure algebra, once a person starts looking for them. A matrix's eigenvalues live inside what's called its characteristic polynomial, built directly from the matrix's own entries. Completely separately, a plain drawing made of dots and connecting lines, a graph in the mathematical sense, has its own attached polynomial too, called its chromatic polynomial, which counts, for any given number of available colors, exactly how many different ways the dots can be colored in, so that no two connected dots ever share a color. Two wildly different sounding problems, matrices and coloring puzzles, both end up leaning on the exact same underlying object, a polynomial, to answer questions that have nothing to do with each other on the surface. A matrix is really just a compact way of writing down a linear map. a rule for turning one vector space into another, arrows in, arrows out, and every fact already covered about vector spaces earlier in this tour applies directly to the matrices that represent transformations between them. Pick a basis for the space going in and a basis for the space coming out. And any linear map at all, no matter how it was originally described, ends up representable as some specific grid of numbers, a matrix. All the linear maps between two given vector spaces even form a vector space of their own, addable and stretchable by the same 8 rules covered earlier, which is a strange kind of one level up move. Vector spaces made out of the maps between other vector spaces, and it holds together perfectly well under the same rules the whole time. The ordinary row times column recipe for multiplying matrices isn't the only way two grids of numbers get combined either. Multiply two matrices of the same size entry by matching entry rather than row against column, and the result is called a Hadamard product, useful in image processing, where two same-sized pictures need to be blended pixel by pixel. Combine two matrices of any size at all into one much larger matrix, built by multiplying every single entry of the first one against the entire second matrix, and tiling the results into a grid of grids. And the result is a Kronecker product, a tool that shows up constantly in quantum computing, since combining two separate quantum systems into one joint system uses exactly this operation. None of these alternate products break the earlier lesson about order mattering. Most of them care about order too, in their own specific ways, once a person goes looking. Even the arithmetic used to multiply matrices together in the first place isn't fixed in stone. The obvious row times column recipe assumes ordinary addition and multiplication sit underneath it. But nothing about the recipe actually requires that specific choice, and swapping in a different pair of underlying operations, replacing ordinary addition with taking the smaller of two numbers, say, and ordinary multiplication with ordinary addition, produces a completely different but still perfectly valid version of matrix multiplication, one used in practice for finding shortest paths through a network rather than for anything resembling ordinary arithmetic. Even the entries inside a single matrix don't have to be plain numbers either. A large matrix can be carved up into smaller subgrids called blocks and treated as a matrix of matrices, with the exact same multiplication recipe applying one level up, block against block instead of number against number, as long as the block sizes line up correctly along the seams. That trick isn't a curiosity. It's a standard load-bearing tool for handling matrices too large to work with directly, breaking an enormous grid down into smaller, more manageable pieces without ever changing what the final answer is guaranteed to be. Somewhere around here, the ground under this whole tour starts to shift, not toward one more fact stacked on the pile, Two are a different kind of question than any asked so far, one that changes what counts as an answer. Every stop up to this point asked some version of the same question. Does a specific formula exist? Does a specific number behave the way it's supposed to? Does a specific operation commute? This next stretch stops asking questions about specific things entirely and starts asking what kind of container specific things are even allowed to live in, which sounds like a smaller shift than it actually is. It takes a clock, an oddly plain one, sitting on a wall doing nothing more dramatic than keeping time to ease into it. Look at an ordinary clock with 12 hours on its face. If it's 7 o'clock right now and 8 hours pass, plain arithmetic says the time should be 15 o'clock, and every clock on earth disagrees because clocks wrap back around to 1 once they pass 12. 15 o'clock and 3 o'clock are, for a clock's purposes, the exact same time. That wraparound has a formal name, modular arithmetic, and the modern version of it was worked out by Carl Friedrich Gauss in the same book already mentioned twice now, Disquisitiones Arithmeticae, published in 1801. The formal rule is that two numbers are congruent modulo some fixed number called the modulus if their difference divides evenly by that modulus, with nothing left over. 15 and 3 are congruent modulo 12, because 15 minus 3 is 12, which divides evenly by 12 exactly once. Waiting 8 hours twice in a row, 16 hours total, lands a clock in the same spot as waiting 4 hours once, since 16 and 4 are also congruent modulo 12. Addition, subtraction, and multiplication all still work inside this wraparound system the same clean way they always have, and a whole clean piece of algebra survives the trip. Division is trickier. A number only has a genuine reciprocal inside a given modulus if that number shares no common factor with the modulus itself, and when the modulus happens to be a prime number, every non-zero number below it automatically qualifies, no exceptions, which turns out to matter more than it sounds like it should. Modular arithmetic isn't some obscure corner of number theory kept alive purely for its own sake. It runs real infrastructure. Public key cryptography, the system that keeps a password or a credit card number private while it travels across the internet, is built directly on top of modular exponentiation, raising a number to a huge power and then reducing the result modulo, some enormous chosen number. Modular exponentiation itself is a strange enough operation to deserve a second look before moving past it. Raising a number to a huge power in the ordinary way, then reducing the massive result down to its remainder, would be hopelessly slow. The intermediate number involved growing so large so quickly that no computer on earth could hold it in memory. The actual trick is to reduce modulo the target number after every single multiplication step along the way, rather than waiting until the very end, keeping every intermediate value small the entire time. And the earlier fact already covered that a computation done piece by piece under modular arithmetic always agrees with the same computation done all at once and reduced only at the finish is exactly what guarantees that shortcut gives the correct final answer. Two of the most widely used systems for that job, RSA and Diffie-Hellman key exchange, both lean on the same underlying trick that multiplying numbers together modulo some huge number is fast and easy to do, but working backward from the result to figure out what got multiplied without already knowing the answer is hard enough to be functionally impossible with current computers. Given a modulus chosen to be large enough, the gap between how easy that operation is to run forward and how hard it is to reverse is, quite literally, most of what keeps encrypted internet traffic private right now. None of that arithmetic cares what it happens to be protecting. It runs the same whether the message on the other side of it is a bank transfer, a birthday text, or a password nobody wants read out loud, which is a large part of why one piece of number theory quietly ended up underneath so much of ordinary life. The RSA system, in particular, leans on one specific piece of modular arithmetic already covered a moment ago. The requirement that a number needs to share no common factor with the modulus before it can have a genuine multiplicative inverse. Pick two enormous prime numbers, multiply them together to get an even bigger number that gets published openly as part of a public key, and the whole security of the system rests on the fact that multiplying two primes together is fast, while factoring that product back apart into the two original primes without already knowing them takes a length of time that grows explosively as the primes get larger, well beyond anything a computer could finish before the sun burns out. For primes chosen large enough, Diffie-Hellman key exchange, the other major system already named, skips factoring entirely and instead leans on a different hard direction, that raising a fixed number to a huge, secret power, modulo some large prime, is fast to compute forward, but painfully slow to reverse, a problem called the discrete logarithm, which sits in that same hard to reverse family alongside factoring, without either one having ever been formally proven to be exactly as hard as the other. Modular style reasoning even turns up in fields that sound nothing like mathematics at all, wherever something has to be divided up into fixed, discrete chunks with nothing left over cleanly. Apportioning a fixed number of legislative seats across regions of different sizes and working out fair whole number allocations in certain economic and game theoretic models both lean on the same underlying discipline of working with remainders and wraparounds that this entire stretch of the tour has been building up. A related idea, whether a given number happens to be a perfect square once reduced modulo some prime called being a quadratic residue, sounds like a small technical footnote. And there's a clean rule for spotting one, worked out by Euler, that only needs raising the number to the power of half of one less than the prime and checking whether the wraparound result lands on 1. Solving a single congruence like that is fast and routine. Solving a whole tangled system of nonlinear modular equations at once, several wraparound conditions, all interacting together, turns out to sit among the hardest general categories of problem computer science has a name for. The same broad difficulty class that swallows an enormous share of the hardest optimization and scheduling problems that show up anywhere. The everyday version of the same idea shows up in places that have nothing to do with secrecy at all. A trick called casting out nines, taught for generations as a way to hand check long arithmetic by hand, works because 10 is congruent to 1 modulo 9. So, adding up all the digits of a number and reducing that sum, modulo 9 gives a quick, cheap way to spot an arithmetic mistake without redoing the whole calculation. Multiply 47 by 38 by hand, and the answer should be 1786. Add the digits of 47, 4 plus 7, giving 11. Then add those digits again, 1 plus 1, giving 2. Add the digits of 38 the same way. 3 plus 8 is 11. 1 plus 1 is 2 again. Multiply those two reduced digit sums together. 2 times 2 giving 4. Now check the original answer the exact same way. 1 plus 7 plus 8 plus 6 is 22, and 2 plus 2 is 4. Both sides land on 4. So the multiplication almost certainly went through cleanly, all without ever touching long multiplication a second time to double check it. Figuring out which day of the week a given date falls on, using methods with names like Zeller's congruence or the doomsday algorithm, runs entirely on arithmetic done modulo 7. Since a week only ever has 7 days to cycle through, the exact same wraparound principle that makes a 12-hour clock work, just counting days forward instead of hours, and giving a person a way to work out in their head that a birthday decades from now will land on a specific day of the week without ever needing to flip through an actual calendar. Barcodes on books, the ISBN system, use a modulus of 11 or 10 as a built-in check digit to catch typos. A single extra digit tacked onto the end of the code, calculated directly from every other digit in the number that flags a mistyped or misread digit the instant the wraparound arithmetic fails to line up the way it should. A clerk typing a book order does not need to know any of that is happening. The check either passes or it doesn't, with no announcement, the same way it does at a cash register or a library desk anywhere in the world. Bank account numbers across Europe under the IBAN system get checked against the modulus of 97 for the exact same reason, catching a mistyped digit before it sends money to the wrong account. A piece of arithmetic running in the background every single time a payment gets entered online, doing exactly the same wraparound job a 12-hour clock does, just standing guard over somebody's money instead of somebody's afternoon, and doing it without a single person entering that payment ever needing to know clock arithmetic exists at all. None of these systems are doing anything conceptually different from a 12-hour clock. They are all just picking a different number to wrap around. A 12-hour clock a book's check digit, a bank account's check digit, a calendar's 7-day week. Every one of them is running the identical mathematics underneath a completely different surface. And the surface is the only part that ever looks unrelated to the others. Once the wraparound number gets picked, the rest of the behavior is locked in by the same handful of rules covered already, whether the thing wrapping around happens to be hours, dollars, or days. Here is a part that pays off everything else in this stretch of the tour. Take all the possible remainders that come from dividing by some fixed modulus m, everything from 0 up to 1 less than m, and put addition, subtraction, and multiplication back on that finite little collection of numbers wraparound style. What comes back is a genuine, fully functioning number system in its own right, small and finite, but complete, closed under all three of those operations, the same way the ordinary integers are. Mathematicians have a name for exactly that kind of structure, a set with an addition and a multiplication that behave the way integers do. They call it a ring. And when the chosen modulus happens to be a prime number, something extra kicks in. That little finite system stops being merely a ring and becomes something stronger still, a field, meaning every non-zero number in it gets a genuine, multiplicative, inverse, full division included, the same privilege, the rational numbers and the real numbers and the complex numbers all get to enjoy. Pick a modulus that isn't prime and that privilege disappears completely. No partial credit, no near misses, gone entirely the instant the modulus stops being prime. A clock arithmetic system built modulo 6, for instance, has numbers that multiply together to give 0 without either one of them being 0 itself, something that can never happen among ordinary integers, real numbers, or complex numbers. And that single broken property is exactly what keeps a non-prime modulus from ever forming a field. Modular arithmetic has picked up a handful of tidy little theorems along the way, the kind number theory students meet early and then keep running into for the rest of their careers. Fermat's little theorem says that if a prime number p doesn't evenly divide some whole number a, then raising a to the power p minus 1 and reducing modulo p always lands exactly on 1, no matter what a was to begin with, as long as p stayed prime. Euler generalized that same idea to work with any modulus at all, prime or not, using a counting function that tallies up how many numbers below a given modulus share no common factor with it. Wilson's theorem flips the logic around entirely and turns into an actual test for primality, stating that a number p is prime exactly when multiplying every whole number from 1 up to p minus 1 together, and reducing modulo p lands on the modulus minus 1, a strange and fairly elegant fact with no obvious reason to expect it going in. And the Chinese remainder theorem, older than any of those three, lets a mathematician take separate pieces of information, a number's remainder modulo 1 clock size and its remainder modulo a second unrelated clock size, and stitch those two partial clues back together into one single, fully determined answer as long as the two clock sizes themselves share no common factor. Even music leans on this same wraparound structure without most musicians ever having reason to name it. Standard Western tuning splits an octave into 12 equal steps. And once a note climbs those 12 steps, it lands back on a note that sounds, for most musical purposes, functionally identical to where it started, just an octave higher. That's clock arithmetic again, modulus 12. The exact same wraparound already covered on an ordinary clock face, just measuring pitch instead of time. A clock, a barcode, a bank account number, and a scale of music are not four different topics. They are four completely different costumes worn by one piece of underlying mathematics. Ring, field, two small words carrying a great deal of hidden weight. Start with the plainest possible example of what algebra calls a vector space, an arrow pinned down at one fixed starting point, pointing off in some direction across a flat plane. Physics leans on exactly this picture constantly, an arrow standing in for a force or a velocity, something with both a size and a direction attached to it. Two arrows can be added together, tip to tail, and the result is a third arrow. An arrow can be stretched longer or squeezed shorter by multiplying it by a plain number, or flipped around backward by multiplying it by a -1. That's all there is to it. A handful of simple rules about how addition and this stretching operation, called scalar multiplication, are allowed to behave together. 8 rules in total, once written all the way out. Nothing exotic among them. Things like addition, not caring what order the addition happens in, and stretching by one, leaving an arrow completely unchanged. Here's where it gets strange. An enormous number of things that look nothing whatsoever like arrows on a page turn out to satisfy those exact same 8 rules. Every single one of them, without a single exception needed anywhere. An ordered pair of real numbers works the same way an arrow does. Added component by component, stretched component by component, and in fact, an arrow and an ordered pair are really the same object wearing two different outfits. The arrow's endpoint just is the ordered pair. Push that up a dimension, or 10 dimensions, or 1,000, and coordinate spaces built from long lists of numbers all follow the identical 8 rules too. The complex numbers, already covered at length, turn out to form a vector space of their own, a two-dimensional one, sitting over the real numbers, with 1 and I as its basic building blocks, its basis, meaning every single complex number can be written as some real multiple of 1 plus some real multiple of I. And that's the entire vector space story for complex numbers laid out plainly. The exact structure already used to plot them on the complex plane in the first place. Adding two complex numbers, real part plus real part, imaginary part plus imaginary part, is nothing more than ordinary vector addition wearing a different notation. The exact same tip to tail addition already covered for arrows on a page, just relabeled. The whole earlier claim that arrows in a plane and ordered pairs of numbers are secretly identical vector spaces reaches all the way forward into the complex numbers too, without a single new rule needing to be invented to make the connection work. Polynomials do it too, and this is where the pattern starts to feel less like a coincidence and more like something structural. Take every polynomial with real number coefficients, all of them, every degree, all mixed together in one enormous collection. Two polynomials can be added together, term by term, and the polynomial can be stretched by multiplying every one of its coefficients by the same fixed number. Doing both of those things never leaves the collection of polynomials. Add 3x squared plus 2x plus 1 to the polynomial x squared minus 5x, and the sum comes out to 4x squared minus 3x plus 1. Term by term addition, nothing more exotic than that. Stretch that same second polynomial by the number 2, and it becomes 2x squared minus 10x. Every coefficient simply doubled. Neither operation cares in the slightest that these are polynomials rather than ordinary points on a page. And that's the entire point being made. All 8 vector space rules hold cleanly, and this particular vector space happens to be infinite dimensional, since there's no upper limit on how high a polynomial's degree can climb. Polynomials turn out to be doing quiet, load-bearing work throughout calculus 2, for a reason that connects directly back to this same vector space picture. Any continuous function at all, no matter how wild or jagged looking, can be approximated as closely as anyone likes by some polynomial, a fact called the Weierstrass approximation theorem, which is really a statement about how densely packed the polynomial vector space sits inside the much larger vector space of continuous functions, close enough to fill in every gap. Keep going, and it turns out functions do the same thing. Every continuous function defined on the real number line, added together pointwise and stretched pointwise, forms a vector space too, and pushing that idea further into function spaces equipped with their own notion of length and angle, called Hilbert spaces after the mathematician David Hilbert, leads straight back to quantum mechanics, since the wave functions describing a quantum system, already mentioned as living in a complex Hilbert space, are themselves nothing more than vectors, points in an enormous, infinite, dimensional vector space, obeying the exact same 8 rules. An arrow on a page obeys. An arrow standing for a force in an introductory physics class, and a wave function describing an electron's quantum state have essentially nothing in common. On the surface, one is a picture drawn with a ruler, the other a function no one can even fully visualize. Structurally, underneath both sits the identical short list of 8 rules about adding and stretching, discovered piece by piece across 2.5 centuries by mathematicians who mostly were not thinking about either arrows or electrons when they wrote them down. None of this got assembled in one sitting. The roots go back to Descartes and Fermat, who founded coordinate geometry around 1636 by tying points on a plane to pairs of numbers. For the first time, Bernard Bolzano in 1804 introduced operations on points, lines, and planes that served as an early ancestor of the vector idea. August Mobius in 1827 brought in barycentric coordinates. Justo Belavaitis in 1833 defined an equivalence relation on directed line segments that share the same length and direction, calling it equipollence. And under that definition, a Euclidean vector formally becomes a whole equivalence class of matching segments rather than any single one of them. Arthur Cayley introduced matrix notation in 1857, specifically to make working with these structures cleaner. Hermann Grassmann in 1844 studied a version of this barycentric calculus that actually ran well past ordinary vector spaces and into territory now called algebras. The Italian mathematician Giuseppe Peano gets credit for the first modern axiomatic definition in 1888, though he called the objects linear systems rather than vector spaces, and his version of the axioms already allowed for infinite dimensions, even though he did not push that side of the theory any further himself. Salvatore Pintrol picked up that infinite dimensional thread in 1897, and the construction of genuine function spaces by Henri Lebesgue, later formalized by Stefan Banach and David Hilbert around 1920, is where algebra and functional analysis properly merged. The same merger that eventually hands quantum mechanics its mathematical home. Here is the actual payoff, the reason any of this history matters beyond trivia. A vector space, no matter which of these wildly different looking objects it happens to be built from, arrows, coordinate lists, polynomials, complex numbers, continuous functions, gets completely classified up to a technical notion of sameness called isomorphism by exactly one single number, its dimension. Two vector spaces built over the same underlying number system with the same dimension are structurally identical to each other in every way that vector space theory cares about, no matter how different they look on the surface. Arrows in an ordinary flat plane and ordered pairs of real numbers are not just similar to each other. As vector spaces, they are the same object, just written two different ways. A theorem proven once in the language of arrows transfers automatically to ordered pairs to any other two-dimensional vector space over the real numbers that ever gets built without needing to be reproven from scratch even once. Every finite dimensional vector space, no matter how it started out looking, secretly reduces down to one of a small countable list, dimension 0, dimension 1, dimension 2, and on up over whichever field it happens to be built on. Given how strange and different the objects filling out this entire tour have looked so far, arrows, matrices, complex numbers, polynomials, that kind of total, exhaustive classification, a full and complete list with nothing left uncatalogued, is a rare thing for a piece of mathematics to be able to offer. That collapsing is the entire value of the abstraction, and it is easy to undersell how much labor it actually saves. Without it, a mathematician proving something true about, say, polynomials would have to start completely from scratch, rederiving every basic fact about addition and scaling from first principles, the exact same work someone else already finished decades earlier while thinking about arrows on a page. With it, that same mathematician just checks the 8 rules hold once and then borrows every theorem ever proven about any other vector space for free. No matter how different that other vector space looks on the surface, some vector spaces pick up an extra piece of furniture on top of the 8 basic rules, a way of multiplying 2 vectors together to get a third one. And the moment that extra multiplication shows up, the space earns a new name, an algebra over a field. Ordinary three-dimensional arrows in space come with exactly this kind of extra multiplication built in, the cross product, which takes 2 arrows and produces a third one, perpendicular to both, a tool every physics student meets while studying torque or magnetic fields. A stranger cousin of that idea, called a Lie algebra, drops the 2 properties an ordinary multiplication is expected to have. It isn't commutative and it isn't even associative, and replaces them with 2 much odder rules instead, that combining anything with itself always gives 0, and that a specific 3-way looping identity always holds. Lie algebras sound like an obscure detour, but they sit directly underneath the mathematics describing continuous symmetry, the same Lie groups already waiting a little further ahead in this tour, and by extension, underneath a fair amount of theoretical physics. The property that finally lets a vector space get pinned down completely reduced to that one clean classifying number mentioned already, its dimension, comes from a pair of ideas called linear independence and a basis. A handful of vectors are linearly independent if none of them can be built out of some combination of the others. No overlap, no redundancy, each one pulling its own weight. A basis is a linearly independent set that's also large enough to build every other vector in the whole space out of combinations of just those chosen few. Every vector space has at least one basis, and every basis for a given space remarkably always turns out to have exactly the same number of vectors in it as every other basis for that same space, whether that number happens to be 2 or 100 or infinite. That one shared number is the dimension, and it is a single fact responsible for the earlier claim that any 2 vector spaces of matching dimension over the same underlying field are secretly identical objects wearing different clothes. Infinite dimensional vector spaces need one more piece of scaffolding before calculus can be done inside them properly, some built-in sense of distance, so that a mathematician can talk about one function getting closer and closer to another one without that idea turning meaningless. A vector space equipped with that kind of distance, one complete enough that every sequence which looks like it should be converging to something actually does converge to an honest member of the space, is called a Banach space, named for the mathematician Stefan Banach. Add an even richer structure on top, a proper notion of the angle between 2 vectors rather than just their distance apart, and the space graduates into a Hilbert space, the exact setting quantum mechanics needs for its wave functions to live in, since angle between two quantum states isn't a decorative extra there, it directly encodes the physical probability of one state being observed as the other. There are a couple of standard ways to combine two separate vector spaces into one bigger one, and the difference between them turns out to matter more than it first looks like it should. Stack every possible pairing of a vector from the first space with a vector from the second space, side by side, and that's called a direct product, or when only finitely many spaces are being combined, a direct sum, and the two names describe the exact same construction in that finite case. There's a second, stranger way to combine two vector spaces called a tensor product, which doesn't just pair vectors up side by side, but multiplies them together into a new kind of object entirely, built so that any way of combining vectors from the two original spaces in a way that spreads out evenly over addition and scaling, called a bilinear map, automatically and uniquely factors through this new combined space first. There's a nicely self-referential twist sitting at the edge of all this too. Take the set of every linear map from a vector space back into the plane field of scalars it was built over, essentially every way of measuring a vector down to a single plane number. And that whole collection of measuring tools turns out to form a vector space of its own, called the dual space. For a finite dimensional space, the dual space always ends up exactly matching the original one in size. Same dimension, structurally identical, though never in a single obvious, built-in way. Only once a specific choice gets made about how to line the two up. Do the whole trick a second time. Build the dual of the dual, and the finite dimensional vector space lands right back where it started, embedded inside its own double dual, in a way that finally doesn't depend on any arbitrary choice at all. Even Hamilton's quaternions, already introduced a few minutes ago as a strange four-dimensional cousin of the complex numbers, satisfy every one of the 8 vector space rules on their own, just like the complex numbers themselves turned out to be a two-dimensional vector space rather than something set apart from the idea, and loosen the definition of a vector space by just one notch. Take away the requirement that there has to be a single fixed point serving as the origin, the zero vector everything else gets measured from, and the result is called an affine space, a loser structure where positions still relate to each other cleanly, but nothing gets singled out as the center. That looser picture turns out to match how points on an ordinary page actually behave better than a vector space does, since a sheet of paper doesn't come with a built-in origin printed on it anywhere, and the fine geometry built on exactly that looser idea is also where the old geometric folk idea of parallel lines meeting somewhere out at infinity finally gets a clean, formal home. Hold a plane square up and count the ways it could move without anyone noticing it moved at all. Leave it exactly where it is. That counts as one way. Turn it 90 degrees, 180 degrees, or 270 degrees around its own center, 3 more ways. Flip it across a line, running straight through the middle horizontally, or vertically, 2 more. Flip it across either of its 2 diagonals, 2 more still. Add those up, and a square has exactly 8 different ways to land back on itself, looking completely unchanged. 8 symmetries total. Combine any 2 of those 8 moves. Do one and then the other. And the result is always another one of the same 8 moves. Never something new. Never something outside the set. That closed little system of 8 moves is called the dihedral group of the square. It is the cleanest possible entry point into the single idea sitting underneath almost everything covered so far. A group, in the strict mathematical sense, is a set of things paired with one operation for combining them, subject to 3 plain requirements. Combining any 2 members of the set always produces another member of the same set, and never anything outside it. The way a long chain of combinations gets grouped together doesn't change the final result. So parentheses can be dropped without ambiguity. The same associativity property matrices held on to even after they gave up commutativity. There is one special member that changes nothing when combined with anything else, an identity. Doing nothing to the square counts here. And every member has a partner that undoes it exactly, an inverse. Turning the square 90 degrees and then turning it 270 degrees more brings it right back to where it started. That's the whole definition. Drop just that last requirement, inverses, and keep the rest, and the structure loosens into something called a monoid instead of a group, a category. The plain counting numbers under addition, 0, 1, 2, 3, and onward, fall into perfectly well, since there's an identity. 0 changes nothing, and combining stays closed and associative. But no counting number besides 0 itself has a genuine additive partner living inside the counting numbers, waiting to cancel it back to 0. A group is a monoid with nothing missing, every single element accounted for and reversible, and that one extra guarantee is worth more than it sounds like on paper. 3 requirements applied to whatever set of things and whatever combining operation happens to be under study, and none of the 3 care, even slightly, whether that set of things is finite or infinite, whether the objects are numbers, shapes, or something stranger, or whether the combining operation was invented last century or 3,000 years ago. The square's 8 symmetries hit an interesting snag the ordinary integers never run into. Flip the square across its horizontal line first, then rotate it 90 degrees, and the result lands in a different final position than rotating it 90 degrees first, and then flipping it across that same horizontal line. Order matters here. The same non-commuting behavior already covered with matrices showing up again in an entirely different setting, symmetry rather than arithmetic, and for exactly the same underlying reason, combining 2 transformations is sensitive to which one happens first. A group where order never matters at all, where combining moves in either sequence always lands on the same answer, the way ordinary addition of whole numbers always has, gets a special name of its own, abelian. And the name isn't a coincidence or a random label pulled from nowhere. It is named directly for Niels Henrik Abel, the same mathematician from earlier in this tour who proved no formula exists for the general quintic, since exactly this kind of well-behaved, order-independent group turns out to be the building block sitting at the bottom of every solvable group's chain. A mathematician who died at 26 before the word group had even been coined by Galois still ended up with an entire permanent category of them named in his memory. A group can also hide a smaller, complete group inside itself, called a subgroup, and the square's 8 symmetries show this off cleanly too. Take just the 4 rotations out of the square's full set of 8 moves. Leave the square alone, turn it 90, turn it 180, turn it 270, and drop every reflection entirely. Combine any 2 of those 4 rotations, and the result is always another rotation from that same smaller set, never a reflection sneaking back in, and that smaller 4 move set satisfies every single one of the 3 group requirements completely on its own, which makes it a subgroup sitting inside the bigger 8 move group. Shifting that subgroup by some other move in the larger group, combining every rotation with one fixed reflection, produces what's called a coset. And for the square, every reflection combined with the rotation subgroup lands in exactly the same second cluster of 4 moves, meaning the 8 symmetries split cleanly into just 2 cosets, the 4 rotations and the 4 reflections, with nothing left over and nothing overlapping between them. That specific splitting into cosets is where the last major piece of vocabulary comes from, a quotient group, formed by treating each whole coset as if it were a single combined element in a smaller group of its own. This isn't just a bookkeeping trick invented for convenience. It's the exact reason the phrase solvable group means what it means. A group counts as solvable in the technical sense from earlier in this tour if it can be broken down into a whole chain of smaller subgroups, each one sitting inside the last, with each step down producing a nice, simple quotient group at every stage until the chain finally bottoms out. Galois' entire criterion for whether a quintic has a radical solution is a single, precise question about whether that specific kind of breakable chain exists for that equation's Galois group. It does, every single time, for every equation of degree 4 or lower. It provably stops working the instant a stray unbreakable piece, like the alternating group on 5 things, shows up inside the chain, which is exactly what happens, without fail, for the general degree 5 equation and beyond. Every combination of moves inside a group the size of the square's 8 symmetries can be written out completely in a simple grid called a Cayley table, 1 row and 1 column for each of the 8 moves, with every cell showing the result of combining the rows move with the columns move. Reading straight across any single row of that table, or straight down any single column, every one of the 8 moves shows up exactly once, never twice, never skipped, a direct consequence of the fact that undoing any move is always possible. And the table for the square isn't symmetric across its own diagonal. The visible fingerprint, laid out in a grid a person can actually stare at, of the fact that order matters, the same non-commuting behavior already covered with matrices, showing up a third time now, in symmetry rather than arithmetic or grids of numbers. Compare the table to the one an addition-based group would produce instead, say the 4-hour clock from earlier in this tour, and the contrast is immediate. That clock's table is perfectly symmetric across its diagonal mirror images of each other on either side, because 2 plus 3 and 3 plus 2 were never going to disagree with each other in the first place. The squares table refuses that same symmetry outright, and a person could, in principle, tell an abelian group apart from a non-abelian one without knowing a single definition, purely by staring at whether its combination table happens to be a mirror image of itself or not. There's also a practical use for a structure this abstract, one that shows up the moment somebody actually needs to compare two groups that look completely different on the surface. The 8 symmetries of a square and the group built from every way of shuffling, 4 playing cards labeled 1 through 4, while leaving some fixed relationship between them intact, can, in principle, turn out to be the exact same group wearing 2 unrelated looking outfits, a fact checkable in practice purely by matching their Cayley tables cell by cell and confirming the pattern lines up perfectly under some relabeling. 2 groups that pass that test are isomorphic, structurally identical, and once that's confirmed, literally everything already known about one of them, every theorem, every subgroup, every quotient, transfers over to the other one for free without a single new proof required. The full set of every possible way to reorder 3 labeled objects, the letters A, B, and C, say, forms a group 2 with 6 total elements, since 3 objects can be arranged 6 different ways. And that specific kind of group, every possible reordering of some fixed collection of objects is called a symmetric group. This is the exact same family of objects. Galois's permutation groups from earlier in this tour were built out of, just described here, in its own right, rather than tied to any one equation. There's a tidy theorem credited to Cayley stating that every finite group whatsoever, no matter how it was originally built or what it was originally describing, secretly lives inside some symmetric group as one of its subgroups. Every finite group underneath its own particular dressing is really just some collection of reorderings of a big enough pile of labeled objects, symmetries of a square, remainders on a clock, matrices, Galois groups, all of it tucked away somewhere inside a large enough symmetric group. Finite groups also come with a clean counting rule attached to them called Lagrange's theorem, which states that the size of any subgroup sitting inside a finite group always evenly divides the size of the whole group, no remainder. The square's 8 symmetries confirm this immediately, since its 4-move rotation subgroup and its 2-move single reflection subgroups both divide evenly into 8. That single counting fact turns out to have real teeth, ruling out huge numbers of potential subgroups before anyone has to go looking for them by hand, purely on the strength of arithmetic. The same kind of counting shortcut Lagrange's own broader body of work on permutations laid groundwork for decades before Galois picked up the thread and pushed it somewhere Lagrange himself never quite reached. A group with exactly 7 elements, say, can only ever have subgroups of size 1 or size 7, since 1 and 7 are the only numbers that divide 7 evenly, a fact settled instantly, without ever needing to inspect what the group's 7 elements actually are, or how its operation is defined. That kind of shortcut, ruling an entire structural possibility in or out from nothing but a count, shows up constantly once groups become the object of study rather than the tool. And it's a small preview of exactly how much can be learned about a structure while staying almost entirely at arm's length from its actual contents. Groups also come with their own basic vocabulary for how big they are, worth having on hand before moving further. The order of a group is simply its total number of elements: 8 for the square's symmetries, 5 for a 5-hour clock's addition group. The order of one single element inside a group is the smallest number of times that element has to be combined with itself to finally land back on the identity. And Lagrange's theorem, already covered, guarantees that number always divides the order of the whole group cleanly. A group built entirely out of the repeated powers of one single element is called cyclic. And it turns out every clock arithmetic addition group covered earlier in this tour is exactly that: cyclic, generated by repeatedly adding the number 1 to itself over and over until the wraparound brings everything back around. Even coding theory, the practical business of catching and fixing errors in transmitted data, leans on group theory in a way most people who use it every single day never notice. Certain specific finite groups, called Mathieu groups, get used to build especially efficient error-correcting codes, the kind of thing sitting inside CD players and satellite transmissions, catching a scratch or a burst of static before it ever turns into a skip note or a garbled signal. Group theory doing invisible, unglamorous, load-bearing work inside a piece of consumer electronics that nobody buying the device would ever think to associate with the 8 symmetries of a square. There's a strange kind of freedom hiding inside all of this abstraction too, one worth naming plainly. Once a structure gets reduced down to its bare rules, closed, associative, identity, inverses, and nothing else, it stops mattering even slightly what the objects inside it actually are. A group can be built from numbers, from symmetries of a shape, from card shuffles, from remainders on a clock, from the tangled symmetries of a quintic equation's roots. And as far as group theory itself is concerned, none of that variety matters even a little. Every theorem proven about groups in the abstract, purely from the 3 bare rules, lands on every single one of those wildly different seeming examples at once, with no extra work required. That isn't a minor convenience, tacked onto the theory. It's the entire reason abstraction was worth inventing in the first place. Comparing two different groups to each other, checking whether they're secretly the same structure wearing different labels, is done with a tool called a homomorphism, a way of translating every move in one group into some move in a second group, while keeping every combination rule intact, so that combining two moves and then translating gives the same answer as translating each move first and then combining the results. When that translation happens to be perfectly reversible, matching every element in one group to exactly one element in the other, with nothing left over on either side, it upgrades to an isomorphism, and two groups connected by one count for every purpose group theory cares about, as the exact same group just relabeled. The word group itself, the actual English word chosen for this whole idea, was coined by Évariste Galois in the 1830s for the specific permutation group of the roots of an equation already covered at length. That isn't a coincidence sitting off to the side of the story. It is the story, arriving late enough to finally be named. Galois needed a word for the set of ways the roots of an equation could be shuffled around while preserving every true relationship between them, and group is the word he reached for. What took mathematics the better part of the following half century to realize is that the exact same underlying structure, a set of moves, closed, associative, with an identity and inverses, shows up absolutely everywhere else too, not just hiding inside polynomial equations. Arthur Cayley gave the first fully abstract definition of a finite group in 1854, stripped of any particular application, just the bare rules on their own. Camille Jordan pulled together the scattered earlier work, Galois' own, plus contributions from Lagrange, Ruffini, and Augustin Louis Cauchy on permutation groups more broadly into one unified treatise in 1870. Walther von Dyck in 1882 gave the first fully modern axiomatic definition of an abstract group in the terminology of the time, and introduced the idea of specifying a group purely by generators and relations, a short list of building blocks and the rules connecting them, rather than by writing out every single element by hand. By then, groups had started showing up from three completely separate directions at once, arriving at the same idea independently. Polynomial equations, through Galois, Lagrange, and Ruffini, was the first. Geometry was the second, once Felix Klein's 1872 Erlangen program showed that different kinds of geometry, ordinary flat geometry, hyperbolic geometry, projective geometry, could all be organized and told apart by nothing more than which group of transformations was allowed to act on them. And Sophus Lie founded the study of continuous symmetry groups, now called Lie groups, in 1884, building directly on that idea. Number theory was the third route in, with abelian group structures showing up implicitly in Gauss's own Disquisitiones Arithmeticae back in 1798, and Ernst Kummer building groups explicitly in 1847 in an early attempt at proving Fermat's last theorem by tracking how numbers factor three separate fields of mathematics, none of them talking to each other at the start, all independently discovering they needed the exact same abstract object, a set with a combining rule that is closed, associative, has an identity, and has inverses. That isn't the kind of coincidence mathematics usually produces by accident. The scale this idea eventually reached is hard to overstate. One of the largest projects in the entire history of mathematics, the classification of every possible finite simple group, meaning every basic, unbreakable building block that every other finite group can be assembled out of, took decades of collaboration across dozens of mathematicians and was only finally declared complete in 2004, with the last piece filled in by Michael Aschbacher and Stephen Smith. Research checking and refining that proof is, according to people still working in the field, ongoing even now. Almost every finite simple group falls into one of a small handful of predictable, well-behaved families, but not quite all of them do. 26 of them refuse to fit any family at all and have to be listed individually, one by one, called the sporadic groups, and the largest of those 26 outliers is the monster group already mentioned, the one with roughly 8 times 10 to the 53 elements in it. In a strange twist nobody saw coming, mathematicians eventually noticed the monster group's internal structure lines up, digit for digit, with an entirely unrelated area of mathematics. A family of functions from number theory called modular functions, a connection so unlikely on its face that it got the tongue-in-cheek nickname monstrous moonshine before anyone had actually proven it was real. Richard Borchards proved the connection was genuine rather than coincidence, closing out one of the odder, unplanned collisions in modern mathematics. Two fields, the classification of finite groups and the theory of modular functions, that had been developed by entirely separate communities of mathematicians for entirely separate reasons, decades apart, with no expectation of ever needing to speak to each other. Lie groups, the continuous cousins of the finite groups covered so far, carry their own enormous payoff in physics, one formalized by Emmy Noether, the same mathematician who gave rings their modern axiomatic definition. Noether's theorem states that every continuous symmetry a physical system has corresponds to some quantity that stays exactly conserved as the system evolves over time. Rotational symmetry pairing with conservation of angular momentum, symmetry under shifting time itself, pairing with conservation of energy. That isn't a loose metaphor borrowed from group theory to make physics sound more elegant. It is a precise, provable theorem, and it means that every single conservation law taught in a physics class, without exception, is secretly a Lie group symmetry wearing a different name. Energy, momentum, and angular momentum look like three separate rules only because three different symmetries were named on three separate occasions by different people long before anyone noticed they were the same underlying idea wearing different clothes. Groups also turned out to be load-bearing well outside pure mathematics. Lie groups sit underneath the standard model of particle physics, describing the deep symmetries that govern how fundamental particles behave. The Poincaré group describes the symmetries of spacetime itself under special relativity. Chemists use what are called point groups to classify the symmetry of individual molecules. William Burnside wrote the first English language textbook on the whole subject, titled plainly Theory of Groups of Finite Order, part of the wave of work, alongside Ferdinand Georg Frobenius and later Richard Brouwer and Isai Schur, that turned group theory from a tool borrowed for solving equations into a full field of study in its own right, studied for what it is, rather than only for what it was originally invented to explain. Here is where this stops being a list of unrelated facts and starts being the actual reframing this whole tour has been building toward. Go back to Galois, sitting with his equation, tracking every way the roots could be shuffled, while every true relationship between them stayed true. That specific object, the Galois group, is a group in the exact same technical sense as the square's 8 symmetries, no looser, no more metaphorical. And whether that group has a certain internal structure, whether it can be broken apart, step by step, into a chain of pieces simple enough to be called solvable, is the entire reason the quadratic, cubic, and quartic formulas exist at all, and the entire reason no formula for the general quintic can ever exist. Groups are not one more curiosity to file next to negative numbers and matrices. Groups are the machinery running underneath nearly everything already covered on this whole tour, discovered independently by algebra, by geometry, and by number theory, because it turns out all three of them, at bottom, kept running into the exact same shape. A group only tracks one operation. Add a second operation, one that interacts properly with the first, and a different kind of object shows up. The same object already met briefly back at the clock. A ring is a set carrying both an addition and a multiplication, built to behave the way the ordinary integers behave. Addition that always has an identity, 0, and always has inverses, negative numbers, combined with a multiplication that spreads across addition the normal way, A times the quantity B plus C always equals A times B plus A times C, the same distributive law that forced negative times negative to equal positive back at the very start of this tour. What a ring doesn't require, and this is the whole point of naming it separately from a field, is that multiplication has to commute, or that every non-zero element gets a multiplicative inverse. A ring is allowed to be missing either one of those, and plenty of the most useful rings in mathematics are missing both. The integers themselves are the plainest possible ring the one every other ring gets measured against. Take the four remainders that come from dividing by 4, 0, 1, 2, 3, and do arithmetic on just those four numbers, wrapping around whenever the count passes 3 or drops below 0. And the result is a small, complete ring in its own right, called the integers modulo 4. 2 plus 3 in that wraparound world equals 1, not 5, because 5 wraps back around to 1. 3 times 3 equals 1 as well, not 9, since 9 wraps around to 1. That's the exact same clock arithmetic from a few minutes ago, just with a different sized clock face. And it's a genuine functioning ring either way. Square matrices form a ring too, and this is where the earlier non-commuting behavior gets its proper name at last. 2 by 2 matrices, added and multiplied the normal way, satisfy every ring requirement. An identity for addition, inverses for addition, multiplication spreading across addition correctly, and multiplication that flatly refuses to commute, exactly the way it refused to commute back when this tour was watching alone one shift from one corner of a grid to the opposite corner, depending purely on multiplication order. That refusal isn't a strike against calling matrices a ring. It's expected. Rings were never required to commute in the first place. Only the friendlier subclass called commutative rings gets that extra promise, and matrices were never signed up for that subclass to begin with. Polynomials form a ring as well, adding and multiplying them the ordinary way, and continuous functions do too, added and multiplied point by point. Ordinary place value notation, the kind used to write down any whole number at all, is itself secretly a polynomial in disguise, worth noticing once and then never quite unseeing. The number 205 is really 2 times 10 squared plus 0 times 10 to the first power plus 5, a polynomial in the number 10, evaluated at 10, with the digits standing in for the coefficients. Every time anyone has ever written down a number using ordinary digits, they were plugging a specific value into a polynomial and reading off the answer, whether they ever thought about it in those terms or not. Change which number gets plugged in for the base 10, and the same digits mean something entirely different. Binary, the base 2 system every computer runs on underneath its screen, is that identical polynomial trick evaluated at 2 instead of 10, and the byte of data is really nothing more than a short polynomial with 0 and 1 for its only allowed coefficients. Even something as far from ordinary numbers as a collection of sets can form a genuine ring if the two operations get picked cleverly enough. Take every possible subset of some fixed collection of things and define addition as the symmetric difference of two subsets. Everything that's in one set or the other, but not both, and define multiplication as their plane intersection. Everything the two sets share. Run through the ring axioms with those two operations, and, a little surprisingly, every single one of them checks out cleanly. That's specific construction has its own name, a Boolean ring after George Boole. And it is a strange one, since in this particular ring, every single element multiplied by itself just gives that same element right back, a property most rings never have, and one that makes a Boolean ring behave less like ordinary numbers and more like a genuine piece of logic dressed up in ring notation. A field is what happens when a ring gets one extra, fairly demanding promise attached to it that every non-zero element has a genuine multiplicative inverse, meaning division always works for anything except zero. The rational numbers are a field. The real numbers are a field. The complex numbers, already covered, are a field too, and that promise of full division is exactly what let complex numbers absorb every quadratic equation's negative discriminant without ever getting stuck. The plain integers, on the other hand, are a ring but never a field, since no integer besides 1 and -1 has an integer reciprocal. There is no whole number that multiplies by 5 to land back on 1. And the clock arithmetic from before draws the exact same line with total precision. Wrap around a prime number, and every non-zero remainder gets a genuine inverse, a full field. Wrap around anything that isn't prime, and that promise collapses because two numbers that are each individually non-zero can multiply together and land right back on zero, something that can never happen in a genuine field. And the whole system falls one full rung down the ladder, from field back to plain ring. Wrap around a prime instead, and every non-zero remainder finds its partner. On a 5-hour clock, 1 times 1 gives 1, so 1 is its own inverse. 2 times 3 gives 6, which wraps around to 1, so 2 and 3 are partners. 4 times 4 gives 16, which wraps around to 1 as well, so 4 is its own inverse too, the same way 1 is. Every single non-zero remainder on that 5-hour clock, 1, 2, 3, and 4, has exactly one partner waiting inside that same small, finite world, with nothing left over and nothing missing, a complete working field with only 5 elements in it total. Compare that to a 6-hour clock instead, where 6 isn't prime, and the machinery jams almost immediately. 2 times 3 on a 6-hour clock gives 6, which wraps around to 0, meaning 2 non-zero remainders multiplied together to produce 0, the exact broken behavior that ordinary integers, real numbers, and complex numbers never allow. Neither 2 nor 3 has a working partner on that 6-hour clock at all, and the whole system collapses from a field down to a plain ring the instant the modulus stops being prime. Prime-sized clocks are not the only finite fields that exist either. For any prime number and any positive whole number power of that prime, there is exactly one finite field of that size, no more, no fewer, unique up to relabeling, even for sizes like 4, 8, or 9 that are not themselves prime. A field with exactly four elements exists, built a little differently from ordinary clock arithmetic, and it behaves in every formal sense exactly like the rational numbers or the complex numbers. Closed, consistent, every non-zero element with a working inverse, just with only four elements total to work with, rather than infinitely many. There's a clean chain running underneath all of this. One long staircase of increasingly strict promises. Every field is a ring, but not every ring is a field. Somewhere in between sit integral domains, rings where at least that last troublesome habit, two non-zero things multiplying to zero, is finally forbidden, even without every element being guaranteed an inverse. The ordinary integers, being the textbook example, keep stacking on stricter and stricter promises, and eventually the staircase narrows all the way down to fields, then narrows one final step further into algebraically closed fields, fields where the fundamental theorem of algebra's promise that every polynomial equation has as many roots as its degree actually holds. The complex numbers sit right at the very top of that particular staircase. The plain integers sit several rungs lower, structurally weaker, but every bit as real and every bit as useful for what they're built to do. Rings have their own version of the subgroup idea already covered, called an ideal, a specially chosen subset that swallows anything the rest of the ring throws at it, meaning multiplying any ideal member by literally any ring element, not just other ideal members, always lands back inside the ideal. The plane multiples of 2 form an ideal sitting inside the whole ring of integers and dividing the whole ring by that ideal, collapsing every even number down to 0 and sorting everything else by whether it's odd or even, produces exactly the clock arithmetic ring from a few minutes ago. Remainders modulo 2. That is the actual mechanical process generalized behind every piece of clock arithmetic already covered in this tour. An ideal getting divided out of a bigger ring to leave a smaller wraparound one behind. Not every ring that fails to be a field fills the exact same way either. Push the requirements up almost all the way to a field. Keep the promise that no two non-zero elements can ever multiply together to give 0, and drop only the very last demand that absolutely every non-zero element gets a working inverse, and the result is called a division ring. The clearest example of one that isn't also a full field is Hamilton's quaternions, already met a few minutes ago. Since every non-zero quaternion does get a genuine inverse, full division really does work. But quaternion multiplication itself refuses to commute. A, B generally doesn't equal B. A, which is precisely the one property standing between a division ring and the stricter definition of a field. There's a tidy, almost surprising cleanup theorem sitting at the small end of that same idea called Wedderburn's Little Theorem, which states that any division ring built from only finitely many elements is automatically forced to be commutative after all, meaning it has no choice but to already be a genuine field. Non-commuting division rings, it turns out, are only possible once infinitely many elements are allowed into the room. Field extensions are the exact mechanism that was already doing quiet work back during the compass and straight edge stretch of this tour, now finally given its full name. Take the rational numbers and adjoin, meaning bolt on, the square root of 2, and the result is a bigger field, one that contains every rational number plus every combination of a rational number added to a rational multiple of the square root of 2. That bigger field sits directly on top of the rational numbers, the way a second floor sits on top of a first. And the straight edge and compass proofs from earlier were really proofs about exactly how tall a tower of these floors can ever get built purely by taking square roots, one floor at a time, doubling in size at every single step, never allowed to triple. Stack 2 of these floors on top of each other, and the tower can spring a surprise. Adjoin the square root of 2 to the rational numbers, then adjoin the square root of 3 to that, and the resulting field turns out to contain every combination of a rational number plus a rational multiple of the square root of 2 plus a rational multiple of the square root of 3 plus a rational multiple of the square root of 6 thrown in as well. A fourth square root nobody explicitly adjoined at all, showing up for free simply because the square root of 2 times the square root of 3 multiplies out to the square root of 6. And despite being built from 2 separate steps, that whole 2-floor tower collapses down into a single simple extension, after all, generated entirely by one number on its own, the square root of 2 plus the square root of 3 added together. That's not a coincidence specific to this example either. It's a general fact called the primitive element theorem that any tower of field extensions built with ordinary arithmetic, the kind used throughout this entire tour, can always be collapsed down to a single generating number, even when it took several separate steps to build in the first place. There's one more wrinkle worth sitting with, because it's the kind of thing that sounds like it shouldn't be allowed to happen. Build a field out of the rational numbers by adjoining a solution to the equation x squared minus x minus 1 equals 0, an equation whose 2 solutions are the golden ratio and a second related number. There are 2 different ways to match that abstract field up with the real numbers. One, sending the newly adjoined element to the golden ratio itself. The other, sending that same abstract element to the golden ratio's numerical partner instead. And both matchings are equally valid, equally consistent, with nothing inside the field itself able to say which one is the real one. The abstract field doesn't come preloaded with a preferred answer. Which concrete number the abstract symbol turns out to mean depends entirely on which embedding gets chosen, a strange kind of ambiguity sitting underneath a huge amount of algebraic number theory. Galois' entire theory from earlier in this tour runs on the same floor plan. A Galois group is underneath its permutation description, actually tracking the different ways of climbing up and back down a tower of field extensions like this one, while leaving every rational relationship between the roots undisturbed. Rings, fields, groups, and field extensions were never four separate stories being told back to back. They were one structure, looked at from four different rooms in the same building. The word ring itself, in this specific mathematical sense, was coined by David Hilbert in 1892, published in 1897. According to one historian's account, Hilbert reached for that word because these structures had a habit of circling directly back to themselves, in a very literal sense. Take an algebraic integer, a number satisfying some polynomial equation with whole number coefficients, and raise it to higher and higher powers. And every one of those higher powers can always be rewritten as some fixed whole number combination of a small handful of its own lower powers. The powers cycle back endlessly, the way a ring itself has no end to circle around, and Hilbert's name for the structure stuck immediately. That same negative number construction from the very start of this tour, pairs of counting numbers bundled together to build negative numbers out of nothing but subtraction waiting to happen, is, in fact, the single most basic working example of a ring that exists anywhere in mathematics. The plain integers themselves, built exactly that way and studied as a ring ever since. Richard Dedekind had gotten there earlier without using the word at all, introducing the term ideal, borrowed from Ernst Kummer's earlier notion of an ideal number in 1871, while studying the ring of integers belonging to a number field, though Dedekind never once used the actual word ring for the general setting himself. Abraham Frankel gave the first fully axiomatic definition of a ring in 1915, though his version of the axioms was stricter than the one used today. Emmy Noether gave the modern axiomatic definition of a commutative ring in 1921 in a paper called Ideal Theory in Rings, and effectively founded the entire branch of mathematics now called commutative algebra in the process, a branch that has since become one of the load-bearing walls underneath algebraic geometry and algebraic number theory. Both, there's a direct line running from that ring of matrices, already covered, straight back to the vector spaces covered just before it, and the line runs through exactly the linear maps already introduced. Every square matrix of a given size sitting over some fixed field is really just one more way of writing down a linear map from a vector space back into that same vector space. And the entire collection of those self-maps, added and composed together, forms what's called an endomorphism ring, with plane matrix multiplication playing the role of the ring's multiplication operation. That single fact threads three separate pieces of this tour into one. Vector spaces supply the objects. Matrices supply the concrete grid of numbers representing a transformation of those objects. And the ring structure explains exactly why those grids add and multiply the way they do, including why that multiplication was never going to commute in the first place. The same reason ordinary function composition never commutes doing one thing and then another, almost never matches doing them in the reverse order. Polynomial rings turn out to be one of the more productive places this entire structure gets put to work, and one particular payoff loops all the way back to matrices one more time. Every square matrix has an associated polynomial called its minimal polynomial, the simplest polynomial equation that matrix satisfies. And because the ring of polynomials happens to have unique factorization, the same guarantee ordinary whole numbers have, that minimal polynomial always breaks down into a specific, predictable product of smaller, irreducible pieces. That breakdown is the actual engine underneath a result called the Jordan canonical form, a theorem that says any matrix, no matter how messy it looks at first, can be rewritten in a specific, simplified layout once the right coordinate system gets chosen, and the entire proof of that fact leans on treating polynomials as a ring and factoring inside it exactly the way whole numbers get factored into primes. Rings sort into a whole spectrum of niceness, nested inside each other like a set of increasingly strict dolls, running from the plain integers at the loose end all the way to a full field at the strict end. And the terminology for that spectrum is worth having on hand. A ring where two non-zero things can never multiply together to give zero is called an integral domain, the plain integers being the classic example. Push further and demand every element vector into primes in one single, unavoidable way, no alternate factorizations lurking, and the ring becomes what's called a unique factorization domain. Push further still, requiring every ideal to be generated by one single element rather than needing several, and it becomes a principal ideal domain. Each step tightens the screws a little more, ruling out one more kind of pathology until there's nothing left to tighten and the ring simply becomes a field with the strictest fields of all, the algebraically closed ones, already covered, sitting right at the very center. Rings that behave nicely enough in an entirely different sense get their own name too, Noetherian, after Emmy Noether, meaning a ring where no chain of ever-growing ideals can keep climbing forever without eventually stalling out. There's a mirror image version too, an Artinian ring named for Emile Artin, where it's the shrinking chains rather than the growing ones that are forced to stall out eventually. It turns out, somewhat surprisingly, that every Artinian ring is automatically forced to be Noetherian as well, a one-directional guarantee that took real work to establish and doesn't run the other way, since the plain integers are Noetherian without being Artinian at all, an infinite descending chain of ideals inside them, each one dividing evenly into the last, that never once bottoms out. The plain integers are Noetherian. So is any polynomial ring built over a Noetherian ring in the first place. That single finiteness condition, no infinite climb, turns out to be exactly the property that keeps huge swaths of modern algebraic geometry and number theory from spiraling out into cases too wild to ever classify. Ring, field, two more words added to the pile sitting next to group and vector space, each one picked up along the way at the exact moment it was needed, and then set back down. What none of them have been allowed to do yet is stand still, side by side, long enough to be looked at together. Go back to the very start. 6 divided by 2 times the quantity, 1 plus 2, 9 or 1, depending purely on which convention for reading juxtaposition got taught first, and both conventions are sitting in real textbooks right now. So there is no hidden third answer waiting to settle the argument. That fight was never really about numbers. It was about notation straining past the point it was ever designed to hold, and professional mathematicians mostly step around it entirely by writing fewer division signs and more parentheses. Underneath that notation fight sat a much bigger one. Negative numbers spent well over 1,000 years being called absurd, by name, in print, by mathematicians who kept using them anyway because the arithmetic demanded it. 0 took centuries to graduate from an empty placeholder mark into a number a person could actually compute with. Imaginary numbers got settled with an insulting name in the 1500s, and never once had it changed, right up through building the mathematics underneath quantum mechanics and modern electrical engineering. Matrices broke a rule multiplication had never broken before, in front of anyone who ever learned that 3 times 5 and 5 times 3 were always the same number. Every one of those was treated at some point by working mathematicians as a rule to memorize rather than a fact anyone could explain. And in every single case, decades or centuries later, there turned out to be a real reason underneath the rule the whole time, sitting in place, waiting for the right piece of abstraction to finally make it visible. Then there is the other kind of strangeness entirely, the kind with no explanation waiting to be found later, because there is nothing left to find. No formula, built from the 4 basic operations and roots of any order, can solve every possible degree 5 equation, and that was proven, not merely unfound, by Niels Henrik Abel in 1824, with the actual mechanism behind the proof handed over by Évariste Galois before he turned 21. No straight edge and compass construction can trisect an arbitrary angle, or double the volume of a cube, or square a circle, and that was proven by Pierre Wansel and Ferdinand von Lindemann in the 1800s, using the exact same underlying algebra Galois had used on equations, just aimed at geometry instead. Both of those are permanently closed doors, not hard, not still open, closed, with the proof itself standing where the door used to be. And running underneath everything on this entire tour, doing the actual load-bearing work the whole time, sat 4 structures that kept showing up again and again under different names, because they were never actually different things to begin with. A group is whatever collection of moves stays closed under one operation, with an identity and inverses waiting inside it. Whether those moves are shuffling the roots of a quintic equation, or the 8 ways of turning a square back onto itself, or the vast, still only partially mapped collection of symmetries hiding inside the standard model of particle physics. A vector space is whatever collection of things can be added together and stretched by a plane number while still landing back inside the same collection, whether those things are arrows pinned to a page, ordered pairs of real numbers, polynomials of every possible degree stacked together, or the complex valued wave functions quantum mechanics uses to describe where a particle probably is. A ring is whatever collection of things carries both an addition and a multiplication built to behave the way whole numbers behave, whether that collection is the plain integers, the remainders left over from dividing by a fixed clock size, or a grid of numbers that flatly refuses to multiply in the same order twice. And the field is a ring with one extra promise attached, that division always works except by zero, a promise the rational numbers keep, and the real numbers keep, and the complex numbers keep, and the plain integers never could. That is the reframe this whole tour was walking toward from its very first sentence. Modern algebra, the version research mathematicians actually work inside of today, stopped being about solving for x a long time ago. It stopped being about numbers at all, in any specific sense. It became the study of exactly those four skeletons: group, ring, field, vector space, and almost nothing else, because it turned out that fully understanding those four abstract shapes already explains the quadratic formula and why it stops at degree 4, and why negative times negative is positive, and why a clock only forms a full field when its size happens to be prime, and why two matrices can multiply to a completely different answer just by trading places. None of those were separate mysteries. They were the same small handful of skeletons, over and over, wearing a different costume every single time, and the costume was the only part that ever looked new. This is also the actual answer to a question that never got asked directly along the way: why algebra keeps expanding its own definition of what counts as a number. Negative numbers got let in once mathematicians noticed the integers formed a working ring, whether anyone approved of them philosophically or not. Zero got let in once the same recognition landed. An additive identity a ring simply can't function without. Imaginary numbers got let in once the field promise, division always working except by zero, turned out to demand them, whether the name stuck around as an insult or not. Matrices, meanwhile, never had to fight for admission at all, because nobody ever expected them to behave like ordinary numbers to begin with, only to behave like a ring, which they always did. Non-commuting multiplication included. Every one of the old fights this tour opened with: absurd numbers, useless numbers, mental torture, was really a fight about whether a specific object was allowed to count as a legitimate citizen of one of these four structures. Once the structure said yes, the old insults just sat there, permanently attached on objects nobody doubted anymore. There's a plain, cheap way to say the whole thing in one line. Algebra spent its first few thousand years asking what a number is. It spent its most recent 150 asking what a structure is. And that turned out to be the more useful question, the one that had been sitting underneath every earlier answer the entire time, waiting to be asked directly. None of that makes the first few thousand years wasted effort. Nobody could have jumped straight to groups, rings, fields, and vector spaces without first sitting through centuries of arguing about negative numbers, without Cardano's mental torture over square roots of negative quantities, without Galois losing sleep over which equations could be solved and which couldn't, without generations of Indian, Islamic, Chinese, and European mathematicians, each nudging some small piece of the picture a little further along before handing it off. The abstractions came last because they needed something concrete to abstract away from. Take away the messy centuries of specific fights over specific numbers, and there would have been nothing left to build the structures out of. That six and that two and those parentheses from the very start still don't add up to one single correct answer, and they never will, not because mathematics failed to settle it, but because the question was never really about mathematics to begin with. It was about a choice of notation made by humans for the convenience of humans, and different humans made different choices. Everything else covered along the way, every proof, every structure, every insult that outlived the insult itself, was mathematics doing exactly what it has always done, finding the rule underneath the mess, once the mess has been sat with for long enough.